All right, good afternoon. So my name is Mohit, and we'll start the tutorial today on the dot at 1:30. So if I go back to the previous slide, sorry. Yes, so I'm the second guy over there. Unfortunately, Ghassan could not make it today. So this is the third time this year we are doing this tutorial. The first time was in WACV, second time was in AAAI, and today is the third time. And for whatever reason, the logistics have worked out in such a way that in WACV, I was the one who gave the tutorial. Ghassan was the only one who went to AAAI to give the tutorial. Unfortunately, today he's not there, and I'll be the one who'll be giving the tutorial. We have about an hour of break in between, about 3 to 4 p.m. So that is going to be a welcome time for my voice, essentially. So I wouldn't have to go the entire continuous 3 hours talking through. Just in terms of logistics, we can try to make this as informal as possible. So if anybody has any question in between, please feel free to just stop me and just ask me any questions. If something is unclear, I'd be more than happy to go through it again. If you just came in now, so the tutorial materials are available online. And by materials, I mean the slides I'll be using. There are about 170 odd slides. A few of them are hidden, but there should be about 160 slides that we'll have to go through today. That technically means about a minute per slide, but there are many slides which basically are more transition slides. So it's not going to be as heavy as the number of slides implies. In terms, so there's going to be about 5 parts. There'll be an introduction, and then the 3 major things that we'll talk about today, which is the idea of explainability, uncertainty, and intervenability, followed by a very small conclusion section. The most important thing that I would like to emphasize at the start is the idea of robustness at inference. So whenever we talk about deep learning models and machine learning models, we generally think of it from the perspective of how do I do the best possible training? What is the best data curation that I can do in order to make the biggest and the best neural network possible? But technically, I come more from a signal processing, electrical engineering perspective. And there we always played with the idea of sinusoids. We started off thinking about sinusoids, and then we went to cosine, DCT, those kind of transforms, where essentially our models were fixed, and we kind of projected on top of these models in order to see how best we can understand the signals. And all the algorithms that were put on top of that, the sensitivity, robustness, and those kind of stuff, came more towards the inference side rather than developing the models themselves. So most of the things that we'll discuss, actually, a lot of things are motivated from that perspective, where we are more interested in the robustness aspect at inference once the network has been trained, rather than thinking about how we can help the robustness in the initial stages of a neural network cycle, which is going to be at the training phase. All right, so let's start off with a meme, basically. So when we think about deep learning and neural networks, we have this expectation of what a neural network is going to turn out to be. But at the end of the day, it might not be that. It might not be the thing that you expected to start with. And this is very common in meal prep, especially the first time you start doing something, you start training neural networks, it is going to be very hard to get the right, let's say, recipe in order to get the best possible neural network or deep learning algorithm that is possible. So the expectation versus reality in deep learning is something that exists, and we have to contend with. And a few years back in Vision, this was a very common example that we were using on the right-hand side over here. But if you look at these things, this is, some of us have to do a double take, essentially, by looking at individual images over here, looking at which of them are cupcakes versus which of them are dogs, essentially. And the reason I think is quite clear, because there is a lot of overlap in terms of image statistics and features between the two. We have to spend a couple of seconds looking at them and thinking, okay, which one is a puppy versus which one is a blueberry muffin, right? This is something that we have to do. We have to introspect and we have to see. But again, if you feed this right now to ChatGPT 3.5, I believe, it should be able to give you the exact names right now. But this is a classic example of what we mean by robustness for these kind of deep learning algorithms. It's not just adding a little bit of noise, but rather it's very easy to confuse these algorithms based on the kind of images that you feed them. On the left-hand side is some simple tricks that we can do on top of images that will again confuse neural networks. The stop sign, a network would have learned on this kind of a stop sign. Every single time you feed the stop sign in, it will give you the best, it will give you the right prediction. But as soon as there's a little bit of changes, let's say a shearing effect on the right hand side, it doesn't know what it is looking at. Even though very clearly we can see it's a stop sign, it thinks it's a racket. And it makes sense, right? If you look at a tennis racket or any other racket, it's usually placed in that position, in this sheared position. So you'll be able to see what it would look like. Same thing at the bottom here as well, a manhole cover versus a pretzel, when very clearly it is not. So this is basically what we mean by expectation versus reality when it comes to robustness. The best laid plans of sensors and networks often, they go out basically. So we engineers, usually we try to say this and use this as an excuse, but it should not be. We have to have neural networks that are robust, that do their job well. All right, so let's introduce this entire session by thinking about what it is that we want from a neural network. Any deep learning enabled system, they must predict correctly on novel data. This is the goal of any inference. If we have spent a ton of money basically trying to train networks on a huge amount of data, we expect that the neural networks should be able to look at these challenges and still get the predictions correctly. So I think at this stage, you're seeing dirty lens at different progression. So this is a data set that from a few years back where the German traffic sign recognition database was taken, and then we added a few challenges on top of these things. So in this particular case, what you're seeing right now, I believe, is some kind of an additive noise that has been added. And this is a progressive noise. So there are about 5 levels of this noise, and all of them are essentially on top of these data. What we noticed was that as soon as you train neural networks on good data sets with very pristine images, but as soon as the novel data sources come into picture, which is the anomalous data or out of distribution data, adversarial data, networks generally tend to not perform well. The results decrease drastically. And if our goal is to look at this from the perspective of training, if you're thinking that what you need to do is train better, it's not as straightforward as that. So let's think about what we are looking at. So we want a robust algorithm, which is basically going to be robust towards novel data. So let's say we have that novel data at training itself, which again makes it non-novel, not novel, but still let's assume that it's possible that we get this kind of novel data at training. So what happens in that case is you have to now make a decision. Where do you use the novel data during the training process? So, you have a couple of choices right now. The first is you use it in initial training. In the beginning, when you're training the first, let's say, a few epochs, you use this kind of a novel data. The results are not going to be as good as you want it to be. The reason being that, let's look at this image over here on the top right. Let's say I'm using the most simplest data, the most low information data that is possible. If I have this distribution and the red dots are the data that I have access to. It's very easy for a network to learn this kind of a classifier, this kind of a decision boundary, when you have low information data. But as soon as you have data which is on, let's say, the edges, which let's call it novel right now, the kind of a decision boundary you're going to learn is going to be very, very different than the one you want it to, right? So you want your decision boundary to look something like this up top. But when you have access to only these red bubble data, this is how your decision boundary is going to look like, which in essence, what happens is your performance based on the amount of samples that you have chosen, and if you've chosen all novel data, is going to decrease drastically. This basically means that you should not give a high weightage to novel data during the early training stage. So does that mean that the opposite is true, which is we train with all simple data in the beginning and then include novel data at the very end? And the answer is not true. And it's not good to do that as well, because we have this entire concept called catastrophic forgetting, where if you're trained on one data set on a particular task, it does extremely well on this blue task, let's say, with 100% accuracy. But as soon as you introduce a new task or new data set, the results on the new data set increase as well. So this is after 50th epoch, you are training your network, and at 50th epoch, you introduce a new data set, which is here in the green. So as soon as you introduce a green data set, what happens is that your results for the green data set increases, but the blue data set suffers. So you see that the classifier accuracy now decreases from around 100%, it goes down to around 20%, which is problematic. This is not how it should be. So catastrophic forgetting is something that happens and which is very problematic. And this occurs because we introduce novel data at the end stage of a neural network training cycle. Again, all of this is to motivate the fact that novel data essentially packs this kind of a 1-2 punch. So first off, novel data, it may not be available during training itself. And in fact, the definition of novel data is that it's not available at training. Even if available, novel data does not easily fit into either the earlier or later stages of training. We just saw this. It's not easy to know when and where to introduce your novel data during the training procedure if it is still available. So again, the goal of the entire tutorial is to basically talk about this one thing, which is that we must handle novel data at inference. And again, the novel data sources can be test distribution, anomalous data, and so on. This is an actual example, by the way. Like, we always know, or we have always seen traffic signs, stop signs, red stop signs. But if you go to national parks, you'll see green stop signs. So this is something that an autonomous vehicle must be capable of detecting, even though there is a huge difference in color from red to green, primary colors. It should still be able to see that essence of the traffic sign is that of a stop sign. So the goal for us is we must handle this novel data at inference. So just to go over the contents of the tutorial. So this was just an introduction into what we'll be looking at. We'll have 5 parts. The first part is going to be just talking about an introduction into inference in neural networks, followed by the 3 important parts, which is explainability, uncertainty, intervenability, and then some just a very short, about 10-15 minute conclusions and future directions. So we started at around 1:30. At 3 o'clock is when we'll have the first break, around 3 to 4. We'll start again at 4, and hopefully we'll be done before like 5:15, so that we have enough time later down the line to just to discuss, and if anybody has any questions. Again, if anybody has any questions in the middle, please feel free to interrupt. All right, with that in mind, let's start with part 1, which is going to be about inference in neural networks. So we'll have about 5 parts here, which is the basics of neural networks, some robustness aspects, an introduction into what information we are interested in, some challenges at inference, and gradients at inference, and how that relates to the information that we'll be discussing. So deep learning, I think all of us are very familiar with. The goal in visual deep learning, at least, is to extract some kind of features, very simple features to start with, these kind of edges, these kind of colors. But as soon as you move forward to the intermediate layers, these features combine themselves in some fashion, in some nonlinear way, in some convolutional way, or in some attention-based way, in order to give us a different kind, a broader set of features, essentially. And as soon as you come to the higher level features, you have more semantic meaning that you can associate with each of these features, on top of which, if you train a classifier, you will be able to discriminate if your goal is classification or generative modeling or any kind of a head you can put on top of your representation space. Underlying computation unit, we are very familiar. The simplest possible arithmetic mechanisms, which is just summation of simple weight multiplied with the data module, with the weight, and then a nonlinear activation function. In this case, it looks like a sigmoid, but most of the cases there can be other activation functions that can exist. Of course, there's a bias as well to make sure that your data is centered, your features are centered. We stack as many of these neurons as possible on top of each other and next to each other to construct multiple hidden layers, so that we'll have output layers. And if you give a cat image in the beginning, you will get the output as a cat at the very end. So this is a very, hopefully everybody is familiar with artificial neural networks and neural networks in general. The goal of these 3 slides was just to showcase the fact that very simple functions, very simple arithmetic functions occur within these neural networks in order for us to go from this large image into a single word, which is cat. These hidden layers are where the initial representation, the low-level features, mid-level features, and high-level features are coming from. All right. So the progression that happened in the last few years essentially has taken these very steps, these very simple protocols and very, very simple arithmetic operations, and now have converted them into billions and trillions of parameters. I think this is GPT-3 is 1 trillion in 2022. Last year, I believe when GPT-4 came out, it was 1.76 trillion parameters, even though it was more of an ensemble rather than a single network. But essentially, the number of parameters are very, very high right now, which is 1.76 trillion. Again, the primary reasons for these advancement is because of the expanded interest, of course, in the research community, the computational resources that are available, and the availability of big data as well. All right, so let's think about what we mean. So until this point, we discussed about architectures and training, but when we say inference, we are given a network, large-scale neural network that is trained. We are given an image, and in terms of classification, we require a prediction. That is all that we need. Our network here is a trained network, so it has all the information that is present in the large data sets that you started with, and our goal is to get some kind of a prediction in the case of discriminative classifiers, which we have been talking until now. So let's say I have the image of a cat here, which is an X. I pass it through a network that has been trained. I get a certain amount of logits that I can use in order to get some kind of a class probability. Logit is essentially the output from the last fully connected layer, and I can put some very simple statistical tools like softmax classifier or a softmax function in order to convert it into this kind of a probability, where I can say with about an 89% confidence that the image belongs to that of a cat. Again, the data that I'm choosing for this purpose, at least in this example, it's not novel, because the network has already seen this data. The network has not this particular example, but an instance of a cat before. But let's say I'm choosing a different data. It's still a cat. We all know this is still a cat, but this is basically an animated character from the movie Puss in Boots, right? So in this particular case, the data is novel because the network, while it knows what a cat is, it has not been able to understand or see the features that is provided in this particular cat. So this is what makes the data novel, which is the idea that the image features are not something that was seen before within the neural network. Again, a robust neural network deep learning process is going to correctly predict the class even when the data is novel. Even when these animated images are not seen by a neural network, it should be able to classify it. So to achieve robustness at inference, there are a few things that we require. The information that is provided by the novel data is a function of the training distribution. So I can't just make this into something like very weird, like Picasso kind of drawings, and give it and expect the network to again classify correctly if it doesn't know the meaning of what a Picasso drawing is going to be. I'm talking about the weird triangular shapes. There still has to be some statistical correlation with the training distribution. We also need a methodology to extract information and techniques that utilize the information from novel data. Now, why is novel data challenging? So in the next few slides, we'll go through a very simple analysis or try to understand what it means to describe why inference is challenging on novel data. Whenever we talk about this idea called subspaces or manifolds or representation spaces, we tend to show these diagrams here on the left-hand side. When we show these diagrams, we know exactly what the topological definition of this mathematical manifold is. I can go into Python, I can go into MATLAB and feed in an exact equation, and I can generate this manifold here on the left-hand side. To do that, I need that exact mathematical description, which we do not have when it comes to a neural network. A neural network, a deep learning algorithm, is empirical in nature. We have huge amounts of data points, sometimes billions of data points that we can use to train trillions of parameters. So getting this kind of a mathematical function is next to impossible. When we do more data visualization from the neural network perspective, you've probably seen these kind of images on the right-hand side. What this is nothing more than about 10,000 different data points that have been used in a dimensionality reduction technique. In this case, it was isomap, to construct this kind of a manifold. That is what you're seeing here on the right-hand side. So what do I need access to? I need access to that 10,000 different images or data points in order to generate this kind of a manifold on the right-hand side. But at inference, we don't have this, right? Because if I go back here, what we have at inference is one trained neural network, one image, or one data point. That is it. We'll not be able to construct these kind of manifolds on the left-hand side because we don't have the mathematical function to derive it, nor can we construct this kind of a manifold on the right-hand side because we don't have the 10,000 data points in order to describe it. So this becomes very challenging. So that's why inference is challenging. Inference on novel data is going to be challenging. So let's say on the right-hand side, we have access to our billion data points. So that basically means that whenever we have this kind of a novel data point that comes in the 72nd epoch, let's say, or it's the 72nd data point in my batch, I still will have access to all the data points at training to kind of try to understand where this novel data fits in. I can change my network based on the gradients. I can do many kind of things on the right-hand side during training. But at inference, we don't have that ability because we don't have access to that huge amount of training data, right? So trained network knowledge is not easily accessible. Again, we have access to a network model that has been trained, but it's not in the form, a nice form that we can use in order to construct these nice representations of novel data. What we have is an unknown distribution of unknown parameters, and this trained network knowledge is not accessible for us at all. This is what makes this kind of inference very challenging, especially on novel data. So what can we do? And this is where the idea of information comes into picture. I started by saying that we'll talk very quickly through the neural network portion, and we'll discuss about the information that is required. Now, there are different kinds of information. If this were more going into a more information theoretic point of view, we would start off with Shannon information, we would start off with mutual information, and then probably come to the next one, which would be Fisher information. But we're not going through that process. At inference, we have access to a trained network and a single data point. And the best kind of information that we can get in this particular setup is what we would call Fisher information. Fisher information is essentially the surprise of us in a system that observes an event. We won't go through the derivation, of course, but essentially the idea of this information is given by the right-hand side, the equation here on the right-hand side. What we do in Fisher information is that we don't have access to the distribution itself. So we don't know how this distribution exists. Rather, what we do is we assume something about this distribution. Let's say some aspect theta. Let's just call it the mean. Let's just say this kind of a complicated manifold is nothing more than a simple Gaussian distribution. And Gaussian distributions, you just need two things in order to define Gaussian distribution, a mean and a variance. Let's just say that theta is equals to the mean in this particular case. And the way I would define Fisher information is just by taking the gradients of some likelihood function, which in this case would be a Gaussian distribution, taking multiple instances of this measurement of mean and taking a variance across it. And this is the kind of information that we are going to have access to based on a single data point and the network. Now, the network we have access to, which basically means that the theta, which I was talking about before, is a parameter of that particular network. So if we take a gradient with respect to that parameter, whichever parameter within the network, you will be able to get some kind of information through your system. And that is the kind of information that we are looking for at inference, which will help us in the when we are dealing with this kind of novel data. Now, a very, very important, a key statement that I have not motivated yet, and it's not very obvious at this point, is that at inference, given a single image from a single class, we can extract information about other classes. And that is possible because of the gradient information, the Fisher information. Now, this statement will be, I'll bring this back a few slides later down the line when we discuss explainability, because it's much, much easier to see it in these kind of visual explanations rather than by looking at equations. But this is a very key piece of information, which is that at inference, again, we are only given a single image, a single network, and yet we'll be able to derive information about multiple other classes based on this single image using the network via Fisher information. The goal of this slide is basically to motivate the last portion over here, which is that gradients, they draw information from the underlying distribution as learned from the network weights. So the kind of theta parameter that generally is associated with the likelihood function, we are now talking about it from with respect to a neural network parameter. So if you're familiar with Bayesian neural networks, then theta is essentially the, if you're taking a Bayesian neural network to be some kind of a Gaussian distribution, then theta can be that. Again, that is only if you're interested in more Bayesian perspective, but if not, it's perfectly fine to just think about this theta as nothing more than some parameter of your neural network, let's say the last fully connected layer. And if you take a gradient with respect to some likelihood function or some function, you will get some information out of it, which is going to be your Fisher information. We'll bring back these things, the variance decomposition, throughout the other parts. Again, we are starting off with this kind of analysis in terms of information perspective and inference. But at the end of the day, we, in the next part, which is explainability, we'll bring back everything we just discussed, especially this sentence over here, to try to discuss why this is true by looking at more visual explanations of what these results are going to look like. All right, so why are we so interested in the idea of gradients? So gradients infer information about the statistics of underlying manifolds. I think this is something that we can all agree at this point, which is that we don't have access to an analysis or information within the manifold. If we want to understand the manifold itself, given nothing more than a single data point and network, what we would have to do is try to understand these gradients or obtain these gradients. So for instance, what gradients give us is this kind of a local information. When it comes to explainability, this is the kind of images that we'll be seeing, the visualizations we'll be seeing. Given this, I'm not sure how easy it is to see this in all the blue covered regions, but essentially this is a very well-known image in computer vision, which is the cat dog image. This here is is an image of bull mastiff. If you pass this through a VGG16, it gives you the correct class. And if you have a certain explainability technique and you ask it, why did you predict this as a bull mastiff, it kind of highlights this region, which is the face of the dog. Essentially, what it is doing is that it is showing us the different features on top of which this image projects itself onto. So in this case, you can probably think that this image, this region around this point of embedding, is where the features of the face of a dog reside. It could be the jowls, it could be the mouth, the teeth, the snout. All of these features reside in this part of the manifold. Even though we won't have access to it, what we can see here is that when it is near to the point, when it embeds itself near to this region, we know something about the local regions of within this particular manifold. So gradients draw information from the underlying distribution as learned by the network weights. Another key, so this is the key property of gradients, which is that it provides local information about the vicinity of X, even if X is novel. Now, even though, let's say that particular dog is something that the network has not seen, it does not matter. It still has to project itself somewhere within the neural network manifold. So it projects itself, and wherever it projects itself, we know something about the locality around it. Now we can again use gradients in order to find a little bit more regarding the neural network manifold itself. So we know that up to a certain linear condition, we can say alpha. This is something that we use via backpropagation, where we add a small constant alpha, multiply the gradients, and then add it or subtract it from the weights, right? So up to a certain very small linearity condition, we can expect a certain amount of information that we can gather from this manifold. The next thing that gradients help us with, another key property, is the direction of steepest descent. We use this a lot during training. Given a huge amount of data, we can get the gradients from all these factors, and then we can say that the weights have to move in a certain direction, or in the direction of the gradients, because we know that gradients essentially are looking at the direction of steepest descent. It will give us the best possible route in order to get to the local or the global minima. So if we have three paths, path 1, path 2, and path 3, what a gradients give us is it tells us which direction should the optimization process go towards, which is knowing, should we, is this local information enough? Is a different kind of information that is required. So negative of the gradient provides the descent direction towards the local minima, and this is measured by this loss function, which is L of theta. Now, the problem again at inference is that we don't have access to what L of theta is. So this is something that we'll come across when we talk about uncertainty. We have to come up with these kind of pseudo loss functions in order to understand how we do this at inference. So this is essentially how we'll be looking at this manifold. We start off with the manifold knowing nothing about it. We know that there is some novel data here on the top. We know it doesn't project itself directly on top of the manifold. We have to do something in order to understand about this manifold. And there's two things that we're going to do. One is we are going to try to construct a different kind of a manifold, what we'll call either a counterfactual or a contrastive manifold, to try to understand how the data point can move to this new contrastive or counterfactual manifold. Or we can traverse through the representation space by doing some kind of an intervention within this data. That is what you see here on the right-hand side. So by doing these things, we can get some kind of an idea about a manifold that we have no access to at inference. All right, with that, we come to part 2, which is going to be about explainability at inference. So this was more of a setup, which is the idea is that given this kind of unknown manifold, how do we extract enough information?
Hey, Jacob.
No. I'm sorry, I heard something online on Zoom. If you have any questions, feel free to stop me anytime. Yes. So the question was why we have no access to manifold at inference. So the idea is that at inference, we are given one data point and the neural network itself. Now, we have no knowledge about how that neural network is trained, what assumptions are made while training the neural network. So it's just a bunch of 1.1 trillion parameters that is stacked in a certain way. So we don't have any either mathematical description to get it, or we don't have data points in order to project on these parameters to get this on the right-hand side. Yes, yes. So at deployment, let's say as a user who is for the first time looking at ChatGPT, I have no idea how it has ever been trained. So that is the point of view that we are going with. I'll talk about it. It's basically we don't have access to the ground truth, so we need to come up with our own ground truth in order to construct that loss function. But yes, that's a very good question. We'll spend a few slides talking about what that means. Yes. Mhm. Yes. So I think so if you go here somewhere in the back, we talk about here in the loss, but then we move on towards more of a likelihood function. So the feature is more from a likelihood perspective. So given this kind of a likelihood manifold, that is where the features exist. Loss, you're absolutely right. You wouldn't consider that to be like a feature perspective for the loss, but it's the change in that feature which you could consider as a loss perspective. Maybe it'll become clearer when we talk about explainability, because it's there. We have more of a contrastive perspective that we can actually show in terms of what it means. Yes. Generally, it's more gradient of the parameter, like the theta parameter. So in this case, it could be gradient of the final fully connected layer or gradient of the final convolution layer that we would do. There are instances, I have a couple of slides where we do gradient with respect to data, but that more comes towards the adversarial perspective. We create these adversarial noise and we add it. And the addition is, in fact, this kind of gradients from the data perspective. Yes, we are always assuming that there is a maximum likelihood perspective for prediction. Yeah. All right. So now let's talk about the part two, which is explainability at inference. So we'll talk a few things about what visual explanations are and specifically concentrate more on the gradient-based explanations. In this case, it would be GradCam and some variations of this GradCam, which is counterfactual and contrast cam, and then have a more case study. Um, so let's start with the idea of visual explanations. It's something that most of us are probably familiar with. It gives us this kind of a saliency map or a heat map that shows us why the network predicted what it did. Again, it's not a causal explanation. So here we are not calling it observed causal, we are calling it observed correlations rather than causal factors or causal heat maps. This is not the reason a particular neural network did what it did, but it's what the network thinks is important for its prediction. And that differentiation is very, very important, especially when we come to part number 4, which is intervenability. So the best way to think about these kind of explanations is to think of it in terms of questions. So in this case, if I were to show you an image of a bull mastiff, I can ask the question of why bull mastiff, and the heat map would show you this kind of image of the dog, which is the face of the dog. I can ask you, what if bull mastiff was not in the image? Then your answer should be that I'm going to probably say that it's a cat, because just consider that nothing of the dog features are here. So the only interesting part of this image right now is the cat, and hence that is what would be used in order to create this kind of a prediction, which is cat. The last one is I'll ask the question of why bull mastiff rather than a boxer. And there are a couple of things answers here. One, yes, the cat exists. And two, if you see here, usually the jowls of a bull mastiff is different from that of a boxer. So that's why I'm predicting this as a bull mastiff rather than a boxer. So that would be more of a contrastive kind of an explanation that you can get. So if the decision is based on visual characteristics within data, we call these things as visual explanations. But a better way to try to understand them is from the perspective of the questions that one can ask. And this is where the context and relevance comes in. You as a user can have these different kinds of questions that you can ask and get different explanations. We'll talk very briefly about how to generate these explanations as well. And this is very important, where the role of explanations at inference for users is very important. Again, we are not considering that everybody who uses these networks is very well versed with what a neural network is. They may know the definition of what a parameter is, they may not. They may know the definition of Fisher information, they may not. It doesn't matter. It could be a kid, basically, where the kid is asking why spoonbill, and the kid needs to be shown this image on the left-hand side and told that, there's a pink, round body, straight beak, everything, in order to teach the kid something about spoonbills. An ornithologist can ask the question, why spoonbill rather than a flamingo? And it has to be more of a relevant explanation for that person. The ornithologist, of course, knows about the pink round body, straight beak. So she's asking you a specific question here, which is why spoonbill rather than a flamingo? And the answer has to be the lack of S-shaped neck. So basically what you're doing is you're assessing whether the network knows about the difference in S-shaped neck and knows about the difference in legs as well. Of course, there could be more existential questions. Why spoonbill rather than a fox? And everything with respect to this spoonbill should be highlighted because, of course, a fox is completely different compared to that of a spoonbill, right? So this basically garners trust within neural network. So the role of explanations has to be contextual and relevant, and that context and relevance is given by the user. And this is very important, right? Because in these days of large language models and multimodal AI, a lot of people interact with these neural networks, and it's very, very important that we give contextual and relevant explanations to these users. The most common way of showing visual explanations is by gradient-based explanations. And the simplest ones are, of course, vanilla gradients, deconvolution gradients, and guided backpropagation. If I take an entire image and I take the gradient with respect to the data, as the question was in the beginning, then we get these kind of explanations, or we get these kind of heat maps, which vaguely resemble that of the original input. You can probably say that the guided backpropagation on the right-hand side kind of resembles, or what you would say is a good explanation. There are a number of works that have refuted this idea of guided backpropagation, by the way, because the reason being that if there was another face on the left-hand side, let's say a human face, that human face would also be shown here in the guided backpropagation explanation, because it cannot differentiate between classes. Your gradients by themselves are insufficient to differentiate between classes. They look at all the interesting features within the image in order to generate these kind of explanations. One way to go past that is by using GradCam, which is probably the most famous visual explanation that exists. It doesn't matter which kind of a computer vision paper you're looking at, if it's on multimodal AI, on just image recognition, VQA, medical images, seismic images, you'll probably have come across this idea of GradCam. The idea of GradCam is very simple. It kind of uses the power of both gradients and activations in order to construct these kind of explanations. So again, this is very important. So let me spend a couple of minutes just going through what is happening within this framework. Let's say I have an image here on the left-hand side. Again, the cat-dog image, bull mastiff and a tiger cat. It passes through a network. A CNN at least is nothing more than a bunch of convolution layers that are separated by some kind of activations and pooling layers and so on and so forth. At the end of which is this kind of a fully connected layer. Just before the fully connected layer, you have these convolution maps. Generally, what happens is that any kind of task, this part of the backbone remains the same. These days, it's not a convolution layer, it's a bunch of attention heads in transformers, but still the output is still the same. You'll have some kind of a map here in the middle where you can use it in order to construct these kind of attention maps and these kind of GradCam explanations. So the final convolution layer, I'm going to use those feature maps in order to construct these explanations. Let's start by looking at the final stage, the fully connected layers here. Let's say I pass the entire image through the CNN and I get the output here. I take that logit function and I backpropagate it. Again, this is not the loss. I'm taking the logit function itself. So think of this as the likelihood function. I'm taking that particular parameter and passing it backwards until I come to the last convolution layer. So that you see here on the bottom. So these gradients at the last convolution layer, all you're doing is you're just global average pooling it. So at every single, you're just adding them up. Question? Sorry? theta parameter, so the final convolution layer. So you're differentiating it with respect to the final convolution layer here. So dou yc by dou aj. I'm sorry. So dou a is activation function, not the parameter itself, but the embedding on top of the parameter, which is the activation function. So we are differentiating with respect to the activation function using chain rule to backpropagate it until we come to the final convolution layer. And once we are at that stage, again, convolution layer is just a bunch of kernels stacked one on top of the other. All of this blue region is global average pooled. I and j is essentially the height and the width to convert into a single number. So the blue becomes a blue, green becomes a green, the red at the left becomes a red. So it's just one number. We're just global average pooling every single parameter within this layer and converting it into a bunch of numbers. What we do here is now multiply it back to the activations. Again, this is the activations. Our gradients are respect to these activations. Now these gradient global average pool gradients are just weighing the activations. It's just telling us which of the activations are important in the initial forward pass. And we are using that in order to convert it into this kind of a GradCam map. So alpha kc, which is the numbers, are multiplying each of these channels, which is alpha k multiplied by a. Your sigma, which is you're just adding all of these multiplications and activations together. You're passing it through a ReLU, which is a rectified linear unit. You're just zeroing out anything that is less than 0. And then that is essentially your heat map that you obtain at this particular stage here. And this is our GradCam explanation. Every time I've showed you this in the previous slides, this was a GradCam explanation. We have passed through this entire process, passed it through the network, differentiated it with respect to the activations, come back to the last convolution layer, multiplied it with the activations, and then summed them all up together to get this kind of a heat map. Of course, the dimensions are different. At the end, you just blow it back up, interpolate it back up to the original size of the image itself, and you'll get this kind of a GradCam. Yes. Yes, exactly. Absolutely. So so this we are showing in terms of a 224 cross 224 image, but for a VGG16 architecture, I believe it's like a 14 cross 14, which has now been blown up to a 224 cross 224. ResNet, it's even worse. It's like a 7 cross 7. So the fine-grained nature of explanations you're not going to get when it comes to these kind of CNNs. But if you try to do this in transformers, the results are much better because transformers don't have this kind of it doesn't decrease as much. So you can have a much better explanation on transformers, or you can directly use attention, but still this could be a different way. So GradCam is used in multiple applications: image classification, image captioning, visual question answering, any kind of a visual data you have access to, and you should be able to get some kind of a visual explanation using GradCam. Again, the only difference, of course, is the head is going to be different. In image classification, we have this fully connected layer. In image captioning versus VQA, visual question answering, we wouldn't have the same network head that would exist over there. So what we discussed until this point was we took the likelihood function, which is basically the logits. You can consider that to be some kind of if you put some kind of a statistical operation on top of it, could be a likelihood function that you have backpropagated a parameter in. And based on that, you're getting this kind of a Y-bull mastiff. Going back to the original manifold example that I was showing, essentially you've extracted some kind of a local information based on that statistic. And that local information has told you that the most important region in the image in order to make this classification has been this, the head of the dog, which is what your visualization is telling you. Now, there could be more contextual explanations that we should generate, right? Which is observed counterfactual and observed contrastive. The way we would do it is what we would call these kind of explanatory paradigms. By making small changes to what we backpropagate, we can get this observed counterfactual and observed contrastive. Let's start with the counterfactual cam, where the goal is now to say that if I did not have this dog in the image, what would the explanation have been? What if bull mastiff was not in the image? Well, the answer would probably be a tiger cat, and this is the explanation. This is the visualization. The only difference from the GradCam framework is that we backpropagate a negative. In other words, we are saying that all the features that existed before, you're now backpropagating without those features. And the fact that you have a ReLU is a rectified linear unit, which essentially zeroes out everything that is less than 0, and it's not used in your framework at all, can now be used in order to construct this kind of a counterfactual CAM where you're losing this features. Again, this is a very restrictive counterfactual. Counterfactuals themselves are a very big topic by themselves. In this very restrictive setting where we are only interested in backpropagating the gradients, we can now say that this is counterfactual CAM, where backpropagating the zeros make it this way. Now, the next one is if we want to ask the question of why bull mastiff rather than a boxer. And again, until this point, we have only backpropagated the think of it as the likelihood, which is the logits. At this point, we want to backpropagate the loss function itself. So instead of backpropagating the likelihood, now we are backpropagating some kind of a loss function. And there was an earlier question, what does it mean by backpropagating the loss? Essentially, what we are doing is asking the network, what is the difference between some class prediction P, in this case, bull mastiff, let's say, and then Q, which is some contrast class we'll define, which we have defined it to be a boxer. So why bull mastiff rather than a boxer is some loss function. I think cross entropy loss was used here because it was usually used in the training phase as well. So by just using the cross entropy loss between bull mastiff and a boxer, we can now, it provides us the features that are the difference between P and Q. Again, this could be a boxer, and the reason it could be a boxer is because of the dog face. But the reason that it's a bull mastiff and not a boxer is because of the jowls that is shown here at the bottom. So this is very important. The differentiation between these two, when you backpropagate the loss function versus what happens when you backpropagate the logits themselves, is very important here. You're backpropagating some function of the difference between features rather than which of the features has made it a boxer or a bull mastiff. Same thing when we were showing the why spoonbill rather than flamingo. This was the exact thing. We were backpropagating the cross entropy loss between a a spoonbill, which was a prediction, and some contrast class Q, which was the flamingo. And we would, of course, get this kind of visual explanation at the end. Now, there are multiple reasons why we would use something like counterfactual CAM and contrast CAM. So let's look at, we already looked at the top. Given an input image of a spoonbill, we can say GradCam is because of all these features that exist. If we were to ask the question, why spoonbill rather than flamingo? Why spoonbill rather than flamingo, then essentially it needs to showcase us this kind of neck. Again, this is just a representative image we are showing. It's very important to note that during inference, we only have access to this spoonbill image. We have not shown it, during inference, we have not shown it the flamingo. It has knowledge of the flamingo. Our goal is just to extract that knowledge and say that the difference is in this S-shaped neck. Same thing with all the other contrastive explanations as well. We can ask, why spoonbill rather than a pig, and essentially all the regions of your spoonbill have to be showcased. Now, many parts of this particular images are very understandable. Like we know about the spoonbill. If you look at the Bugatti convertible, this is a Bugatti convertible. If we ask why Bugatti convertible, then some regions are highlighted. If I ask why convertible rather than coupe, then the roof of the car is highlighted, which is important, which is true. That's why it's a convertible rather than a coupe, right? But if I ask the question why Bugatti rather than Audi A6, then all the regions of the car are again there. And all of these are human understandable. So anything until this point that we talked about is human understandable, human interpretable. But there are some things which are same as GradCam. And if you think a little bit more on it, it makes sense. Like if I ask the question, why bull mastiff rather than blue jay? They're very, very different from each other. Right? You don't need to tell me the phylus, the genome, and whatever it is that biologists would say that a dog is a dog, than say something like, oh, look at the face of the dog. It's the most different. So this shows us how a network is making its classification in this hierarchical setting. Now, the more interesting region is to show some non-human interpretable images. So here, the ones in gray, So let's look at this row, for instance. Let's start by saying that a particular network that has been trained on traffic sign database knows that this is a no-left image. And the reason it's a no-left image is because of GradCam is showing us that this kind of a cross exists at this point. But as soon as we ask the question, why no left rather than stop sign, if it were me as a human, the reason I would say it's not a stop sign because it doesn't have the word letters S, T, O, and P. That is the most intuitive way of saying why it's not a stop sign. But the network is showing us something at the bottom left and something at the top right over here. Right? That is where the, if I remove that setting, yeah, you can see that it's something over the top bottom left, which is probably the most highlighted region in this particular image for the question of why no left rather than stop sign. Now, if you look at this and try to understand it, you can understand the bias that exists within the neural network, because the network has learned on these 14 traffic signs. All these traffic signs are the ones that the network has learned on. The only particular traffic sign that has this shape, which is this octagonal shape, is this kind of a stop sign. There is this on the bottom left corner, there is this kind of a straight edge. Top right corner, there's a straight edge. It doesn't exist in any of the other images, in the other traffic signs. So the fact that this exists is sufficient for me to say that the image is only that of the image is not a stop sign. It doesn't matter. It doesn't matter if STOP is not there, if the letter S is not there. It has not learned any of those important, I would say, human understandable, human interpretable features. It has understood something. It's basically a very lazy network, right? It has taken the fastest way down into its global minima and said that since this kind of an edge is not there, it has now learned this. You wouldn't know this by looking at, let's say, a GradCam explanation, like a asking why question. You would only know these kind of biases when you ask different kinds of questions. And that generally happens when you have users who are not engineers, who are not equipped to know that the data set is something like this. It's very common that this happens during inference, that the operational limits are not known by the users. And it's very important for us when we design these networks that we should be aware of these simple biases that may not mean much to us in terms of accuracy, but do exist. All right, so I talked about this very important sentence before, which is at inference, given a single image from a single class, we can extract information from other classes. So let's bring it back right now. So let's say in this explainability study, I ask the question, why spoonbill? And it tells me beak, neck, legs, feathers. Again, yes. Exactly. Yes, absolutely. We have no idea about where that manifold, I would assume that STOP is part of that manifold, but now it's not there at all. There's no reason for it to be there. So in this explainability portion, if I ask why explainability, a network has learned a bunch of features. Let's say it has learned billions of features, beak, neck, legs, feathers. And if I pass a spoonbill image at inference, it's going to highlight these 4 features, your beak, neck, legs, and feathers, in order to say why spoonbill. But if I ask the question, why spoonbill rather than flamingo, then it only highlights the neck, or it highlights that more than the others, right? Again, the network has not seen a flamingo at inference. The only thing it has seen is us backpropagating a loss function between some class, let's say 500 in ImageNet, and then another class which is 525 in ImageNet. We're just taking a cross entropy loss between them and backpropagating that loss function. Without seeing anything from the flamingo class, it still is able to show us. We can extract that knowledge and show that the difference is in this S-shaped neck. And that is what I mean essentially when I say the sentence at inference, given a single image from a single class, we can extract information about other classes. So in this case, without knowing as a user, I wouldn't know what a flamingo is, but I could basically ask why spoonbill rather than flamingo and extract this. And this is an information I could get. Yes. Yes, so you're right. So as an engineer, if I'm trying to develop the system, you're absolutely right. I need to know some kind of a loss function. And I think this has been tested with multiple loss functions. The easiest one was the cross entropy loss, because it is something that the network was trained with. So if all of them are modular, it's very easy then to plug and play, basically say that, it's just all you're giving is the contextually the user is asking this question, and there's already a system that is able to extract this and tell this person. You don't need a knowledge base essentially that tells you the difference between spoonbill flamingo and says that, okay, for this particular image, you need to extract this neck and so on. So there's no big knowledge base that exists between the contrast between the two. It's just that the information stored in the network is sufficient to extract is the main point of it. All right, so essentially, explainability has shown us that there is more information within a neural network than what we can get out from a single image by asking these different kinds of questions and using gradients. So one way that we worked on it about 2 years back in Europe, we had this paper called Introspective Learning. We use this idea of gradients and exporting this kind of new information in order to extract and make a more robust network. The idea was very simple. The idea is about introspection. Now, I started off with this image on the right-hand side. The reason we started off with this image is because we can ask the questions, how would humans resolve this challenge? Well, we introspect. You first ask yourself why you're being shown the slide, why images of muffins rather than pastries. What if the dog was a bull mastiff? Well, there would have been no reason for this particular slide, right? So, it's all different, essentially. You introspect and try to find what the answers are. And this is how we do, as humans, we do it. We don't have this idea of straightforward, feed-forward process. There's nothing called, I sense something and I know what the output is. A kid cannot just say, sense pink feathers, straight beak, and say it's a spoonbill. A kid or any one of us as humans, we reflect on our outputs. We ask ourselves the question, why spoonbill rather than flamingo? Why spoonbill rather than crane? Why spoonbill rather than pig? Once we have answers to all these questions and good answers to all these questions, I can then say that it is a spoonbill. So this idea here on the right-hand side, this entire block is something that is reflection. This is well known in the psychology literature. And this is true, especially when we have novel data. Think of it in your own lives, right? Whenever you have been trained to do something, it's very easy to do that particular work. But as soon as there's a slight difference, you start reflecting on your choices, on your decisions. So that is here on the right-hand side. And essentially, that's what we need to do as well. We need to reflect within ourselves to ask, neural network has to do it when it sees novel data and say that, okay, this is a spoonbill because of the fact that it's not a flamingo because of their shaped neck, and white feathers are not there, hence it cannot be a crane. So these are the kind of things network has to ask itself and to come up with reasons to say that it's not the particular bird that it's looking at. So what we want to do was to simulate this kind of introspection in neural networks. And we define introspection as answers to these kind of logical and targeted questions. Because when you introspect, the first thing that you need to do is find yourself some questions that you can answer to. And what are these possible targeted questions? Well, we already know the answers because we defined explainability this way. We asked why bull mastiff, what if something, or why bull mastiff rather than a boxer. So based on any one of these questions, we can now use that as an introspective feature and establish our introspective network. So going back to those blocks we had before, our goal again is to simulate introspection, but right now we have a more technical definition of everything. That we have a contrastive definition of introspection, which is that introspection answers questions of the form YP rather than Q, where P is a network prediction and Q is some introspective class. We also have a more technical definition where given a network F, some data point X and the network prediction Y cap, introspection is the measurement of change induced in the network parameters when a label Q is introduced as the label for X. This is very important, right? So during contrastive explanations, we just said, take a loss function between some class P and some class Q. Technically, what we were doing back then is tell wrong information to the network. We were telling the network, hey, you have told me this is a P, but in fact, it is a Q. even though we know that that is not true. We knew that it's always a spoonbill. It was never a flamingo. Yet we asked the question, why spoonbill rather than flamingo, just to see what the network would give us, because that is what an explanation is, right? So we want to tell the network, hey, I know your prediction is this y cap, but now I'm giving you a new class. I'm telling you that this is a class Q. Tell me what change you make within your manifold, and that would essentially be the answer for this kind of introspective question. Now, we can do this introspective questions across all possible values of Q to find what our answers are. And we are now coming to the stage where gradients are essentially features in this particular case, right? So till now, we have just talked about gradients as some kind of weights that were helping us giving the explanations. But now we can think of them directly as features. If I were to backpropagate on this very simple MNIST dataset, I know that this is a 5. The ground truth is that of a 5. Now I ask the question, why 5 rather than 0? And if I look at the final fully connected layer, and if I visualize the final fully connected layer, the gradients are there in only 2 spots. One is at the 0th spot, or the class that corresponds to 0. So in this particular network, the size of the network is 50 cross 10, which is the final fully connected layer. The 10 is the number of classes. So MNIST dataset has 10 classes, 0 to 9, which is represented here in the rows. And the x-axis here is the number of parameters within a filter, which is 50, right? So what you see here is that when you backpropagate Wi-Fi rather than 0, the elements within the class that represent 0 are highlighted, and the elements that are present within the class phi are highlighted. Same thing, when I do Wi-Fi rather than 1, you see that anything with 5 are highlighted, anything with 1 are highlighted, and so on. Essentially, what it is telling us is that the gradients change certain filters within my network parameters to make sure that now manifold is changing. So when I bring back the manifold, what you'll notice is that some parts of the manifold where you had local information, which is the phi, has now been shifted to a different spot, which is essentially this kind of a contrastive or a counterfactual manifold. We have constructed this kind of a contrastive and counterfactual manifold. Also, these features are very informative and sparse, as you can see. They only exist within the 0, 1, 2, and so on. There's more theory into why these work. Essentially, when we look at these features, we are not looking at the features directly. It's a combination. So because phi is changing, because it had predicted phi, with respect to phi, what needs to change in 0? With respect to phi, what needs to change in 1? The different contrastive questions you ask is dependent on what the prediction was earlier. So you always have this kind of a YY cap within your framework, and this has to be used within the framework. That is what makes the entire thing more robust.
You signed up for CPR, right?
Okay. I'm sorry, I hear something from Zoom.
I have to deal with it because I have gotten budget for 2 attendants.
Wait, that's fine.
Because you paid already.
And I also want to share some stuff with you.
I want to make sure that I take accountability if I told you, because I need to tell us.
I think somebody's speaking online.
No, you didn't tell me. Because nobody told me to not. And you ask everyone here, so I didn't know that.
If we
I
have
see.
that
Yeah.
fix, with no FRR regression.
Yeah, let's have a.
Okay. Because I got budget for 2 attendances, and I just had to pick 2 people. I picked Kawai and Minping, and I asked them to submit for reimbursement. The rest of the team, I wanted them to hijack their login information.
Oh.
Yes, please mute yourself. Otherwise, it's really hard.
Can you tell us explicitly? I think
that will still talk.
So let me talk to Eslam, see if I can just squeeze this one in.
Okay. Seriously, we are Apple. We have to hijack. We have to argue for this budget.
You are not on that thread. I even I myself, and I want to say 3 people from our team at least go. At least 3 people.
We should discuss on that even now.
Didn't get approved. Not just for our team. Entire Kelsey or a lot of people got dropped. Aslan went
Or I can go
himself
to
in
whatever
person,
I have,
and
and
Matias
then we can
Hernandez.
just have a
That's the
collective
only two people from hands.
So the
So that
politics
we have
thing.
50, 60 people in the org. We need 2 people from Aslan
Okay.
in person.
Okay.
Okay. Okay.
But it's on
We
me. So I
construct
want,
these pseudo
that's how
laws
you're
or these
reimbursed.
pseudo
So
labels,
let me see if I can.
1000,
Like I'll say,
and
I'm
based on
messaging.
that, we can
I
get
said,
some kind of
we want to
features within
participate.
our
I'll let you know. I'll let
training
you know.
Give me a pay raise.
There's more theory into,
Figure this one.
Yes,
this becomes
it was
computationally
this.
very infeasible.
It only had
On
issues
ImageNet,
with
for
one
instance, there could be
place.
1,000 different
I
classes,
was
which
initially
essentially
afraid
implies that
I went
there's
through all the
1,000,000,000,000,000,000
radars, but
thousand of those.
let me actually share the
One of the back
screen,
problems
and maybe if you
very
see
tough
where I am
So there
currently,
are
you could
ways
just
where
give
we
a
can speed
better
this process
feedback.
propagating all these one node vectors. You can propagate all points. And this has been explored before in terms of out of distribution detection. And we can do that. We can back
So I went through
and get a very similar approximation of the contrast.
okay. So I went through another iteration
We can get these.
of the root. So I have the
So for
scripts
every
for
single
that,
image and for
flat
every
file
single
thing.
data,
And based on whatever I heard from
RX2 to RX.
from your feedback,
And we can train a very simple MLP, which is just a 3-layer.
I started playing a little bit around
That
the
we're going to get is more robust than what it would have been without these kind of.
added some restriction on the list mode.
What it means is that introspection essentially provides us with a more robust representation of our outputs. So what I mean by robustness is 2 things. It's generalizable and it's calibrated. Let's spend a couple of minutes talking about each of these. So generalizable essentially means that there's increased accuracy on out of distribution data or novel data. And calibrated essentially means that it reduces the difference between prediction accuracy and confidence. So an ideal neural network, even when it's generalizable and it is calibrated. For an introspective network is that if you have performance accuracy on the y-axis,
And where you have those improvements, but in
there are
terms
many
of
measures of discussing or quantifying this essentially it's the difference between confidence and your accuracy. So ideally you want this expected calibration error to be closer to 0 and you want your performance to be as high as possible. So there is this data set, Cypher10C and Cypher10Cure, where it's a bunch of realistic distortions, at least Cypher10Cure is a bunch of realistic distortions. Cypher10C is all possible, about 19 different distortions that is applied on top of the data sets. Essentially, if you test on these Cypher10C data sets, your resonant accuracy, let's say, from a particular network is going to be around 68 with an expected calibration of about 0.14. But when you introspect on top of it, based on the method that we just discussed, the results increases by large margin. And expected calibration error also decreases, which is essentially what you want. You want all the networks in the bottom left to go here onto the top left. There are other ways, of course, that you can use plug-in approach, which basically means that if you have any kind of a training model, your sensing network, which is the place where you obtain your gradients from initially, it doesn't matter what kind of a way you have trained it, either directly as Resonant 18 or you have a denoising methodology, adversarial training methodology. In all these cases, if you introspect on top of it, the results generally increase. Either the accuracy or the expected calibration error, the results generally increase. There are other applications as well where it increases. Of course, we're not going to go through each and every application, but essentially something like image quality assessment, something like active learning, something like out of distribution detection. Anything that you do after introspection is going to help you. And you're going to get better results in all these cases than if you do it without introspection as your output. All right, so that was about part 2. Yes, question? So for introspective learning, we say that we would have done it initially in the training phase itself, we would have gotten ourselves the introspective network. And at testing, it's still the same thing. We only have access to the original sensing network and the introspective network and one data point. But initially, while you're training the introspective network, yes, you would have used the training data in order to obtain or get out the gradients and then use it for training this kind of a multi-layer perceptron. Yeah. We do. So at the end, when we discuss about intervenability, we have about 10 slides which talk about how we, I mean, it's a very important part of the presentation today, where we'll discuss about how we do this for explanation and how, in fact, they're not good for explainability techniques. Yeah, yes. Absolutely. So the question is, if introspection, it looks like it's almost like data augmentation. So if we do data augmentation with it, are we going to get a similar performance? You're absolutely right. So on the left-hand side here is a simple resonant 18 network that was trained. It got a 67% accuracy. With introspection, it increased a bit. But then you train it with, generally one way of robustness is you denoise your training data itself and you train it. Then you have adversarial train, which is essentially your augmentation. SimCLR, you augment noise. Augmix is more augmentations, essentially. So that means your 67% now changes to 76% with augment noise, right? Which essentially means it has surpassed the 71% that you would have gotten by just introspection. But now if you introspect on top of the augment noise, your results are going to be even more, which essentially implies that it doesn't matter what kind of a sensing network you have. If your sensing network is better, your introspection is going to be better, because the answers to your question of why spoonbill rather than flamingo is going to be more fine-grained, let's say, is going to be better, right? So if your sensing network is better, it will come to a point where introspection is not going to make a difference, which is 89.85 to 89.89. There's no difference at all between the two things, right? So it doesn't matter. If your sensing network is very good, introspective is not going to help you. But in most cases, this is almost like a solved data set. So that's why you have 90% accuracy. But in a lot of deployment cases, that is not the case. Yeah. Yes. Yeah. So this deconvolutional gradients is from the input layer. Essentially, you pass the entire thing through the network, take that one logit of the cat, for instance, and backpropagate it until the very end. So deconvolution essentially means that you have this kind of if you're familiar with more of a unit architecture, it basically is similar to that portion there. That's one way of doing it. There's this another methodology. I think the 2014, the earlier methodology was basically go back in the same way as you do the neural network, except right now the convolution, I believe all the rectified linear units are not there, and instead you're making anything with gradients less than 0 will become 0. So the forward rectified linear units are replaced by kind of a backward rectified linear units. But again, that was back in 2014. But these days, when we talk about deconvolution gradients, it's generally that kind of a unit architecture that exists. Yeah. Yes. So could you repeat that question? Sorry. Absolutely. So that is, I would say that is more similar to like a student-teacher kind of an augmentation framework, where your foundation model is the teacher essentially, and you can use these kind of methodologies where you're just developing a head on top of it rather than the entire feed-forward module that exists. So there have been a couple of works that uses something like that. Yeah. Yes. So that's a very good question. But before I answer that, there was one small difference there. We don't train with corruption. So training is all on CIFAR 10. So even when I was talking about us taking out the gradients here, it was only on the CIFAR 10, not on the corrupted data. So the RX1 to RXM is 50,000. The reason I say 50,000 is because CIFAR 10, the training set is 50,000. So we are not using corruption during the training process itself. We are only using the original data. But to go back to your original question, I think that's an excellent point, which is that on CIFAR 10, there is no change. The results are going to look something like this. I think CIFAR 10 original is like 95% accuracy. The result is going to be 95% with introspection. It does not decrease. It gives the exact same thing. Because what happens is that on these data points, you see that we are extracting for all different classes, like why cat rather than dog, why airplane rather than something else, right? In most of these cases, the gradients are going to be 0, and gradients are going to exist in only one spot. In other words, what is happening is that you don't need to reflect. The sensing is so good with 94%, 95%. Reflection is not going to add anything. There's nothing you get out of introspection, which means that the exact same performance is going to carry forward. And the only place it helps is when this kind of novel data, this corrupted data, let's say, that exists. Yeah. All right, so we have about 10 minutes, and what I'll do is just introduce the next topic, which is uncertainty, and that will carry us to around 3 o'clock. So we'll just cover about 4-5 slides. Now, I'm sure all of you have looked at this image before, the ones on the left-hand side. I've always looked at these images, and I've never been able to see blue and black. For me, it has always been white and gold. I don't know why. Even when people have shown me and told me it does not matter, even when I've put these two here, for me, it has always been white and gold. And this is like a very simple way of trying to understand what uncertainty is. And this is a very well-known visual paradox. Many of you see white and gold, many of you are going to see blue and black, and some of you are going to switch between the two things, white and gold or blue and black. But essentially, when we talk about uncertainty, it's a model knowing that it does not know. I know for a fact that it's supposed to be blue and black, but I can never see it. My visual perception is never going to allow me to perceive some other color, for instance. So this is like a very simple introduction to what is uncertainty. A little bit more complicated. Actually, I still write that it's a simple example. Uncertainty is a model knowing that it does not know. Let's say I have access to certain data points that are represented by this pluses here. It exists between minus 0.5 and 0.5. There's a lot of data points that exist between minus 0.5 and 0.5. So if I were to construct some kind of a simple regression model, I'll be able to do so very easily between these 2 points. But as soon as I pass that range, let's call this the domain, the operational limit, whatever you want to call this. As soon as I pass this particular domain after 0.5, I'm not really sure how this regression curve is going to progress further. It can either go down or it could be a sinusoid function and so on. That's why you see this kind of a region where the regression model might exist. And that is essentially what we mean by uncertainty. A little bit even more complicated example than before is by looking at this sinusoid. Instead of just thinking of uncertainty as, oh, data exists, data doesn't exist, we need to start thinking of, is the model sufficient enough? As I said, I come more from a sinusoid background, so I really love this kind of an example, but essentially that you can describe uncertainty in 2 ways, either data uncertainty, which is aleatoric, or model or epistemic uncertainty. Data uncertainty essentially tells you that there is some kind of inherent noise that is in the data, or your measurement is incorrect. So on the top here, my frequency is off by very, very few points, but in the beginning, you won't notice that. It's almost similar between the 2 functions that have been created. But as and when you progress, the amount of difference between the original signal and the error-borne signal is quite a lot. Right? So that is essentially some kind of an aleatoric uncertainty that can exist. Epistemic uncertainty is I'm not equipping the sinusoidal model with a bias term. Now, if you're familiar with sinusoids, it's always a sine of ft plus some bias that can exist or that should exist. If I'm not equipping my model with that particular bias, then this kind of uncertainty or error is going to exist throughout. So that would be the difference between something like data, which is your aleatoric, or your model, which is your epistemic uncertainty. And this is the last of the introduction slides into uncertainty. But essentially, when we talk about a model knowing what it does not know, what we are discussing is this kind of examples. On the left-hand side here, let's say our goal is a pixel-wise segmentation. So if I look at this output from a network, I know for a fact that this region here is incorrect. This is not how a bus is, right? So even though this is not zoomed in and you don't know the exact pixel-wise differentiation, you can look at the output and say that a bus can never be this way. So what you expect from your network and what you're getting out of the network is not the same. It's in fact very much different than the actual output. So if a network, or if this kind of a prediction is also equipped with something else, which is your uncertainty, and this heat map is essentially stating that any region here near the boundary of the bus, or where the glass reflection is, if I can tell you that there is some kind of an uncertainty that exists within this glass and on this bus, then that basically is a good thing from my perspective, which is that a network knows that any prediction that it has near the glass and near the boundary could be a mistake. And that essentially is what uncertainty is and what we want out of a neural network. All right, so next we come to uncertainty quantification, and I think I'll stop here. We'll have a break. I think CVPR has a break from 3 to 4 o'clock. We're about 6 minutes early, but I've seen in the morning how crowded the places become when we are looking for like free coffee and lunch. So hopefully you guys, you can go and spend 6 more minutes over there and get your coffee and breaks. But yeah, we'll start again at 4 p.m. and we'll pick off from uncertainty portion again. Sorry? Yeah, I think it's a 1 hour break. CVPR has a 1 hour. Thank you. Hey. No. Oh, nice to meet you. Okay. 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 Oh. Okay. Oh, okay. Oh, nice. Oh, excellent.
Yeah, it's very
Mm-hmm.
information.
Oh, yeah.
Visual, I use visual. So I don't know if you can provide any.
Okay.
Yeah, I will contact for share, but we haven't yet decided on the.
Okay, I'll definitely look into it. Yeah, let me take a photograph of your. Oh yeah, I think that is much easier. Yeah.
I will find my card.
But I'll probably take a photograph. I think this will be easier. Yes. Yeah, I'll definitely look into it. Yeah. Thank you. Thank you so much. Hi. Okay.
I'm doing
Okay.
and video.
Which one? In the tutorial website, it's there. I think. Let me make sure it's there. Let me see. So if you scan this, yeah, tutorial slides. So here. Oh, thank you so much. Yeah, definitely. Yeah, of course. Of course. Yeah. Oh. Hey, how's it going? Yeah. Nice to meet you. Yeah. Yeah.
About like your last slide.
Which one? Uh-huh. Uh-huh. Oh, entropy. Like the one that I showed was actually based on like Bayesian neural networks. So essentially we have weights and we have designed like Gaussian distribution for these weights and decided, oh, the variance of this particular Gaussian distribution is this heat map for this pixel, this thing. So that particular example was based on Bayesian entropy, but I think there are other methods of doing that kind of pixel-wise estimation as well for the uncertainty. Yeah. Yeah, for sure. But in tutorial, I think we have designed everything to be like the classification is the easiest. So that's why I think classification is everything we have done. But yeah, the generative modeling as well. We have, but I think this is more very specialized in seismic imaging, where we generate like the distribution of labels themselves, and we use that as some kind of uncertainty map to do this one. But yeah, for I think for classification is maybe easier to this one. Yeah. Yeah, actually, there should be a poster that is going on right now with one of the students from our lab is actually there in that prompting and vision kind of this one that is there. But I'll be here until like Friday, so we can definitely this one. Yeah, I think you said you have like two. Okay. Oh, I'll definitely attend. Yeah. Thank you. See you there. Yes. Yeah. Thanks. Hey.
Great presentation. So, I have a question. For the sake of easiness of presenting and usually work on like implementation models and everything. So this is something that we have when I was working, I've been thinking about and you also said that it doesn't answer the question why something that's just suddenly get.
Yes.
So how do you think that
So in a couple of, when we talk about intervention, I have a couple of slides on the segment anything model, SAM, which basically does very similar thing to this thing. I think there's like SAM plus something is like SegGPT, which does instant segmentation based on like just very simple prompts and stuff like that. So in segmentation, I've always had this, I've tried to reason with myself why we need something like RADCAM within segmentation, because if the goal in segmentation is for us to give that kind of a pixel-wise assessment of a particular pixel being associated with this thing, the output is itself the explanation. So, so I know, but other works which have utilized GradCam within the layers in order to do a better segmentation approach. In fact, I think it's called like a reflective net or something like that in order to give us that this thing. So there are definitely many works that try to do this, but I've never been able to, like if the best explanation is a good local explainer, then that local explainer is itself a segmentation. So the output of a segmentation is probably the best explanation you can find for that object. Right? So I'm not very certain about that answer. Yeah, of course.
Thanks for the presentation. I mean, the first part, okay. So I wanted to ask you about the specific statement because I come from XAI research in Poland, actually, Warsaw University of Technology.
Okay.
If you ever heard about it, you probably know. And like I know it is a tutorial, but there was like a very psychological element of the presentation that you show an explanation and then you say the question that this explanation answers, right? But I see a little problem here because what we are actually doing is we are observing the explanation, and then we are like reading a question that we guess it answers, right? It's like it's not that this explanation was constructed in a way that the question was formulated in a mathematical sense.
Yes.
And the attribution map was optimized to answer the question.
I understand.
It's
Yes.
like fitted by us,
Yes.
right?
Yes.
So I know it's the whole area of evaluating the explanation.
Yes.
And yeah, if you could just talk a bit about how your works relate to it in that sense.
It does. So I can show you So
Okay,
this
you could expand,
idea
right?
of evaluating explanation, I think, is very problematic.
Yeah.
So for me, in fact, I always say that once you have an explanation, it's fine, but you also need to have some kind of an uncertainty with that explanation. Otherwise, it's exactly what you said. We are feeding into our own bias and just confirming our own bias.
Yeah.
So, and all existing evaluation techniques, talk about like 3 evaluation techniques, some kind of masking, some kind of pixel-wise evaluation, some kind of structure-wise masking. All of them suffer from the same kind of a concept, which is that they're only looking at the certain mathematical formulation of uncertainty while removing the others. And in fact, if you're familiar with the idea of RISE, which if you're in explainability AI, RISE is probably one of the a well-known mechanism. By making a very small change to RISE, you can get a very bad explanation.
Yeah.
And a network is not, so our evaluation techniques are not capable of trying to say that this, so it looks, this is worse than this explanation just by a very visual sense.
Yeah.
But an evaluation metric cannot say that. Evaluation metric, in fact, is this is a better explanation than.
But you said that this is better than that.
Yes.
And you said that based on your own judgment.
Yes. No, I'm saying based on localization. If I'm saying that none of the context matters and the only thing that is important is the what do you call it? The object itself, which is, I think, I don't know if it's a shark or a whale.
The assumption, right?
Yes, that is the assumption.
Okay,
Absolutely.
right.
So the localization within the object is a very big assumption.
Yeah.
I grant you that. But that is an assumption that we can make in order to do this kind of an evaluation.
Yeah. It's great. I would like to talk about.
Of course. Yeah.
About you.
Yeah. Drop me an email.
Work, so,
yeah.
Is there any chance to catch you like?
Yeah, I'll probably be here. Yeah. Yeah, sure, of course. Email me, so I'll be here for this one. And that'll be fine.
Great.
Yeah,
Thank you.
of course.
First of all, some of the questions got repeated, but
Yes. Yeah. Yeah. Yeah.
So, in terms of segmentation,
I understand. So, so if we were to taxonomize these explanations, so everything that I've talked about is like a direct explanation. A simple, a kid can see the output and make their own judgments. Oh, they can understand what these explanations are. The kind of explanations you're talking about is more of an indirect explanation, where that indirect explanation can be the parameters here are incorrect. You cannot expect a user to understand it, but someone like an engineer who's working on it will definitely be able to understand. There are a number of indirect explanations, I think, for this thing. Off the top of my head, I can't remember that this. I think LRP works for this propagation something, linear propagation something. I've forgotten the so this thing. I'm pretty sure it's LRP that works for this, and also depends on if you have some outputs like shaft values. Those could also work for this as well. So. Oh. Okay, I didn't know that. Okay.
Okay. But yeah, I'll check it out.
Sure. Yeah. 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 Drop me an email. I think that will be the easiest one.
Okay.
Yeah.
Okay. Because that works out. Okay.
Of course. Yeah.
Thank you very much.
Yep. Hey.
Thank you. Now, what
Okay.
So, my question.
No. So it will be based on gradients. We'll have a method on uncertainty.
Okay.
Yeah.
And the second question is like,
yes.
This kind of
yes.
actually
Absolutely.
So how do you do that? Do you do abstraction?
Mhm. Okay. Okay. So I think that depends on two kinds of uncertainty, right? So in data uncertainty, that is always an issue because the fact that a network is going to look at the fact that there is a difference between the object edges, it will always say that there is some kind of an uncertainty. If you can separate the two things, data and aleatoric and epistemic uncertainty, you will you won't have that issues generally. So if you do,
theoretically,
yes, they should not highlight those kind of issues.
Okay.
Yeah, regions. Sorry, yes.
okay.
Yeah.
Okay. Yeah. Okay, thank you.
Yeah, of course. Okay. How do you mean labeling? Or text?
Yeah.
Yes. Yes. Mhm. So what you're talking about is more of an evaluation of it.
Yeah,
You
yeah,
can
yeah.
do that in a few. I believe the birds data set has the exact thing
Yeah,
that
yeah,
you're
you're
looking
right,
for.
right.
So yes, so
Yeah,
there you can do that particular aspect. But everything I showed did not require that. It's basically just the image and
Yeah.
output. Any of the I think you're talking about that bird. So the list thing that I listed, that I did it myself just to make a point that you have to show these cases. But it could be done. Again, you need data sets which are constructed for that. Birds is one of them, but not most data sets. We cannot do that thing. Yeah. Yeah. Hey.
Basically, I did an advice.
Okay.
In the second. So you talked about what
Mhm.
to then
Mhm. Okay. Okay. Okay.
then that's it.
So you have ensemble features, and then you take those ensemble features into one convolutional network. Okay.
Exactly. Yeah. It depends.
Okay.
The number by
Okay. Okay.
the rest of the
Sure. Mhm.
without, and I wonder how to do it without adding like attention.
Okay.
So I wonder if it's gradient methods.
I have a question. So you're talking about these functions. These are not anchor
They
boxes
are
functions.
as well. The function.
Okay.
So it's
Okay. So essentially, when you backpropagate the gradients, anything that give the largest amount of changes are the ones where this is where the change is happening. So if your goal is to select some of them rather than combine all of them, then selection is, in my opinion, it
so
would be
it's
like
not
that.
the selection actually. I use all of them.
Okay.
Then passive.
Okay.
I use all of them.
Okay.
But I guess that the model gives me a way
Mhm.
to some of the function, like
Sure.
some
Yeah.
of the function.
Yeah.
So I'm trying to understand
Mhm.
that part, like.
I'm trying to think of which is a similar like a network thing, right? So in transformers, you have something very similar where you have multiple attention heads, and from these attention heads, you're essentially doing exactly what you say. You have you're basically combining it in the next layer, right? So that combination is the weight which you're talking about, which they call it attention, but essentially it's a very similar concept. It's just a multiplication of some WQ with something. That's it. So the way they would do it is that WQ, WK is itself the attention part, right? So you don't need gradients at all in that particular
So I
case.
need to add another layer.
No,
That's
yeah, you need that
connected layer.
embedding. Yeah, you need that embedding. Yeah, the fully connected layer, I think, would be the
Which
embedding.
is like
Exactly.
attention.
Exactly. It's attention. Yeah.
Just
Yeah.
to add an attention
That's
layer.
yeah. I mean, you can of course try the backpropagating gradients and getting something out of it, but it seems by the architecture you describe, you're converting it into like a transformer thing, and that embedding is not there, which is what you just said, which is a fully connected layer. Yeah. Yeah, of course. Okay. Oh, okay.
So we are focusing on like working with very noisy LiDAR.
Okay.
And the motivation is that LiDAR is so power hungry. If you could save power by operating them at a very, very low power condition, they will become very noisy, but if you can somehow figure it out to work with that noisy data. So she started looking into this very good learning.
Okay.
And I think I'm wondering, like, have you seen this intersection of the machine learning and curriculum learning where, let's say, we are slowly the challenge of in every iteration, like we more and more challenge.
Yeah.
But learning concepts to make it easier to actually
Yeah.
have you seen a better handling of these challenges by combining the concept of introspective learning or curriculum learning?
Not curriculum learning, but active learning, yes. So, I mean, active learning is, I wouldn't say the same, but it's kind of similar process, right? So where they take a small amount of data in the beginning, and instead of, so in curriculum learning, I imagine you change the loss functions after the first stage, second stage, third stage. In active learning, you just change the kind of data we are doing it. So I've seen works that use these kind of gradient-based methods in active learning, but curriculum learning itself, I'm not very familiar with that topic as much, but I imagine that they would be similar. There's this thing called expected gradient length, EGL, in active learning, which I think could be very helpful in curriculum learning as well.
Right.
There was this one paper I remember where they had used like an autoencoder to reconstruct the point cloud, let's say. Of course, you don't have that spatial coordinates, right? You have that, it's more of a point net, point cloud thing. And based on that, the difficulty of reconstruction, people had used it for this one. And there we could use something like expected gradient length, where we backpropagate the entire new point cloud data. And the ones with the highest gradients are the ones which you will weight your loss functions or something.
Yeah, I think that's my second question about. Yeah. So we are basically handling the point cloud data. A lot of the network that we are, they have some kind of distribution layer in between. So they lose the differentiability at that layer.
Yeah.
Right. But you see some methods which don't necessarily that still can actually apply this concept on these challenging data.
Maybe I'm advocating too much for the transformer, but I think transformers that do this kind of a sequential modeling are probably the future for something like LiDAR data, where if you take CNNs, for instance, you require that spatial coordination to be there, but transformers don't need that aspect. So in sequence modeling with transformers, at least all the newer papers I've seen are coming out with that.
So they're able to handle like the LiDAR data will not have the same number of points every time.
Yeah.
So they're able to
yes, absolutely. So all you need is the token size has to be fixed, and any number of tokens can keep coming in, and we can keep back propagating and finding some.
Can we talk some other time?
Of course.
These are the topics that I'm exactly interested in.
Oh, of course. Yeah, please. Yeah, please drop me an email and yeah, of course. Thank you. Thank you. Hi. Nice to meet you as well. Oh, thank you.
I have like several questions.
Yeah.
Yeah. The first one is you said reading comparison. So you said that is not.
Yeah, that's not causal.
Do you think it would, given a single network, a single network, we have a causal sense?
I think the idea of causality is a very, very strict condition. And I have a couple slides later down the line when we discuss like the evaluation of explainability. It is very hard for me to imagine that something like any explainability method is going to satisfy the conditions of causality. We have like 2 to 3 conditions of causality, right? You need to delete certain thing or add a certain set of features, and you want to analyze based on this particular factor. That kind of do calculus is very hard to do in terms of like visual features. There are approximations of it where people take the foreground, background, and separate, and the causality is only based on the foreground, background, or causal and context features. But that's a very, very big approximation. Yeah, it's very strong assumptions. Exactly. So I don't know if I would be ever comfortable saying GradCam would give you like a causal explanation on kind of pre-trained network.
So you mean if I train network, I can show some features of causal, and then back propagate the features to the input space that causal sense.
Yeah, I mean, so if we have something like a tabular data on a structured causal model, we have a structured causal model and I have tabular data. What you're saying is absolutely right. Like the gradients would represent the causal changes required. So if you delete a particular node and you're back propagating around that node, essentially the change with and without that node would be presented in the gradients, right? You're right. But how do you, so I think it's very hard to now take that, what that node means from like image perspective. We can say, of course, that neck is a feature, beak is a feature, but which pixel does that beak start and which pixel does it end, right? These are the, yeah, I feel it's very hard to, hard to say and hard to contend with what causality means in this particular aspect. Yeah.
So I have another question answering my question. Because I'm familiar with using things and
compete with. So ensemble methods are going to be extremely good. I would say that ensemble methods are probably the best that we can obtain. Everything else is an approximation for that. Gradients is an approximation for that. Monte Carlo dropout would be an approximation for that, and so on. We could, of course, get to that stage, but I don't think we are there yet in terms of quantification. No.
So I look at this.
Yes. Yeah. Oh no, the opposite. Gradients are used when data, you have only a single data point, you can get some kind of this thing.
I mean, so you said
oh yes, the initial model has to be trained well. You're right, absolutely. So at inference, you only need one data point, yes, but initial model has to be trained well. But again, there's a kind of a trade-off, right? As soon as you get to that 90% region, there's not much you can gradients will give you. Yeah, exactly. So your most of the gradients are going to be zero, and only a few gradients are going to exist, which is the same as the original prediction. So you won't get too much out of it. So there's a sweet spot where it shouldn't be 90% because you won't get anything more. It shouldn't be like 5% where it's like, you know, gradients are nothing more than garbage basically. So this one, so it's very good at a certain region of operation essentially. And I would say most of the things that we have right now are in that region of operation, especially during at inference, we have these novel and out of distribution data, they fall. For a well-trained network, these are in that 60% range kind of thing. Yeah.
So you think gradients
epistemic for sure. Yeah. Because we are more interested in how the network model is changing without really thinking of what noise is changing the data to be different, let's say. So it really does not care anything about the data at all. It's only looking at, it doesn't matter if there's any noise in the data. I just want to change my model to incorporate that noise. So it's more epistemic than anything else.
You think there's a connection to the patient?
Of course, yeah. So so this is where I don't talk about it, but essentially we can have these counterfactual gradients, right? Like multiple gradients that can exist, right? So we are taking like this distribution in Bayesian neural networks. That distribution is a Gaussian distribution across the prediction. In this kind of gradients, we are taking a distribution, but across different predictions. So it's like you have a mean here, but then you can have a mean somewhere else. It's still a distribution. So there is a connection to the Bayesian processes.
So for the gradients, it's like that is just a slide over the. So what is that is.
It's not a slide, right? So if I backpropagate something like a chair for a flamingo, so if I backpropagate a flamingo for a spoonbill, it's slight change. But if I backpropagate a chair for the spoonbill. There is a huge difference between the two. So the parameters have to move a very larger, exactly, a larger distance. So you can have a distribution of the parameters space from that perspective as well. Yeah.
Okay.
Thank
you.
Of course.
So far, you've been talking mostly about quantification.
Mhm.
Yes. What's the balance problem?
Mhm. Mhm. Yeah. Wouldn't what you just said work there as well? Which basically you have an estimate of your XYZ coordinates, let's say. The prediction is XYZ. You can take x plus 1, x minus 1, y plus 1, y minus 1. So these are the contrast costs, then you can back propagate backwards. So the position is the class.
Is there a way of mapping it to
Yeah, sure. Any kind of a multinomial loss function can be utilized in this setting. Right? So,
exactly the same problem?
no, 100%. Yeah, it should be that way. Yeah.
Okay.
No.
Thank you.
course.
Introspective learning is the goal that I understand is like for more robustness or like novel or different kind of distribution data. If I have a classification, but I just simply have huge confusion between two classes, this is like something that then I follow.
So, so you only have a problem with two classes.
Like I have multiple classes, just between two classes.
You have an issue. So there was this paper recently which talked about the different kinds of errors. So general error, general purpose error is this idea that the likelihood between a number of functions, number of classes is an issue. What you're referring to is this thing where only two classes are an issue. So given an image, for instance, a particular annotator has labeled one class, but it could have been another class as well. So it's like this margin classification kind of a problem. And that is where introspective learning or gradient-based methods work very well, because you're taking this kind of error between two particular classes. So that means that the features are geared towards only those two classes. So it would be very helpful to use gradients in that particular case. It would not be as good if you have multiple cases.
Just general huge confusion between everything.
Yeah, between everything. Yeah. But if you have just two classes, confusion between two classes, any gradient-based method will be very helpful. Including this as well. Like any gradient-based method would be very helpful.
Yeah. The concept of it does sound like it would help.
Yeah.
Okay, thank you.
Of course. Yeah.
Another thing, I'm just curious, like, because I'm studying Masters in Georgia Tech too. Is there like any kind of chances for research?
So I'm a postdoc there, so I don't have like control over this one, but there are a number of professors who basically do something like this. So you should. The way it usually works in Georgia Tech is that you have to come in and do one semester of like something called like a special problem. But once you're done with that, I think it becomes much easier to go through that. So, so you're coming in from DSO. So yeah, I would suggest just reach out to professors and do a special problem under someone.
Special problem.
Yeah, special problem. 8003 or something like that. So once you do that, I think it becomes much easier to do research. Yeah. Yeah.
Hey, quick question. Sorry, not in the first half, but I was going through the slides and I saw some of the gradient based on certain measurements. I was wondering, have you guys explored using potential learning, like just proposal framework?
Could you remind me?
It's basically they talk about how patient networks have this issue where you have to run multiple inferences, and this is basically like a normal inverse common distribution, but then the parameters of the distribution kind of help towards like it's basically file training. You're acquiring evidence, and then you build this distribution, and then that kind of gives you understanding of epistemic uncertainty, and then you're
I don't think that particular I'm aware of, or maybe I am, but I haven't read too deeply into it.
Okay.
But yeah, I mean, I'm aware of the previous ones, but which basically is just dividing into epistemic and aleatoric based on this one, the Bayesian neural networks itself. But what is different in the evidential deep learning, I'm not really sure what the change part is.
I think they basically just recommend like, hey, so they recommend loss term based on conjugate normal priors, and then they basically talk about like this problem can be simplified or looked upon by considering that you're acquiring evidence and building Gaussians for each pixel. So if it's a segmentation model or a distribution model, that for each pixel you're building like a Gaussian of Gaussian. A distribution of Gaussians.
Okay.
And that distribution that comes out to be a normal system.
Okay.
And then when you train the model enough, you get the data, then you can build a data out of it.
Okay.
But so I had a specific question on that. I wanted to say here was that basically what I'm saying is like with that approach, it does work in some of the cases I'm looking at. I'm looking for a distance transform kind of model for limb detection. And I do see sequencing build, but the aleatoric and epistemic uncertainties are highly correlated. And that's not ideal. And I also tried different things like adding noise to the image to expect higher auditory uncertainty. That's the definition of it. And I do see some signal, but again, they're still highly correlated. Like from your experience, what do you think? Like so my question, like my kind of ask was like, is this something which is not the correct thing that is being learned because these don't correlate? Because I do see some signal in most of the cases, but then why are these very highly correlated?
I think the main reason whenever rhetoric and epistemic is, so I don't know about the specific case instance of attention, but always most of the reasons why your rhetoric and epistemic uncertainty is highly correlated is because of the data set, and it's the easiest data you start with. So that's why people say that, okay, just add noise and then start subtracting the uncertainty subtracting. You're making your job harder. Sorry, you're making the neural network's job harder in a way, so that it's forced to learn more causal factors than it would otherwise. Like if it has learned nothing causal, then everything is uncertain. If there's a perfectly causal model, there's nothing that is uncertain, right? Which is so the easiest way to make some, I don't know if I should say easiest, but the best way to make something as decorrelated as possible is to make the data set even harder, or the method even harder. So train with less amount of data, train with some kind of even worse jittering of data. Let's say take the, you said lane detection, right? Just start with decolorized data, something like that. So make its life as hard as possible, as difficult as possible. So that is the best way you can say that when it's learning something, that means it's learning the important parts of that data. So usually whenever you have correlation between rhetoric and epistemic, it's this. It really, there's no incentive for a network to actually learn the difference between stuff. That makes sense.
Right. So does that also mean it's similar to like less trained model, but on the same data? Does that mean the same thing, or you still want to train them enough to be able to adjust the weights enough?
Yeah. So I'm not suggesting like early stopping or something like that. So early stopping would be it would be more of an uncertainty estimation technique rather than a training technique, for instance. So train as good as possible on a limited amount of data, and construct your loss function in a way to weight it differently, something so that you've made its job very hard, but it's still trained very well. I think the training very well is still important, because if you do an early stopping, you'll get a good uncertainty quantification, but at the end of the day, your performance will be very bad. So that dichotomy is a huge problem. You need to make sure that it has learned something while giving you a good uncertainty. Otherwise, it's always going to give you uncertain outputs while not giving any good kind of result. So you do need very trained network, but it has to be difficult for the network.
Right. I see. Okay. Okay. Thank you. Also, would it be okay if I reach out to you by email?
Sure. Yeah, I think we're fine.
And I can find out online.
Yeah, you can get. I mean, in the slides, if you find it, the first slide should have one.
Okay.
Yeah.
Thank you. Thank you for the talk.
Of course. Oh, thank you so much.
I know I already did the tutorial like you for how I imagine how hard it is.
It gets harder, especially after R. Oh my God. Thank you. That's very kind. Yeah.
I don't talk to you because I know your thoughts.
Thank you.
Good luck.
Thank you.
4 o'clock. 4 o'clock. Thank you.
Like the foundational models, we just have
Oh, okay. And DCS. Okay. Okay. You did. No, I'm fine with it. Yeah. It's nice to know. So do you do a lot of work on uncertainty research? Okay. Okay. We see that taking, I think it's not even this month. Reviews will come out next month in July. July 1st.
Something which was theoretically quite strong, but they like they can't write theorem for being so it got kicked out of 5 years back, so I'm still trying to figure out what to do.
I don't understand that. I feel some shows like it's like
Linear or piecewise.
linear or piecewise. Yeah, I had a similar experience actually. I see when we had a very simple paper. I had this kind of a data model and another model with exactly linearity assumption. It was more like phases of learning, like similar to the initial phase, later phase. So we divided into 5 phases where it was all like a linear piecewise function, but it was rejected from ICM because of assumptions are too strong. For,
Yeah, so we try to prove under some conditions that the calibration properties that comes from and those assumptions are too strong. So I'm trying to relax some or something experimental evidence. It's just that I think I don't want to do the complex practice where there's no creative it may see the light somewhere. I think it's good to have a different angle of it and
yeah.
More like track camera.
I would say I started on the test time inference thing because I was very busy playing models. So I just took the models.
Initially loss function proposed here. I did data augmentation, then loss 1, loss 2, loss 3, and I did go on the stage and say that my loss is
exactly, yeah, same projection.
and then now adaptation or post-op calibration. But unfortunately, at least an adaptation you can explain. Post-op calibration like temperature scaling, uniform distribution. That's one of I don't understand the logic of what temperature. It's a function of data sets. But surprisingly, temperature scaling different there's no theoretical analysis. What makes it so?
But it's hard to get validation data for foundation models.
Yeah.
So how to get that temperature coefficient itself is like
and more so it's like pure samples in general, like all these. So in ECCV, like there was one comment saying that you have results on image like LG because it's faster to run like and you think that is not really happy and this is image like image like birds when you I think that still prefer signal for things which are less solid review unlike
more of a pattern that you keep on submitting until you get
large scale conversation I don't think all those papers will sustain.
There is no option if you don't like
Just want to increase the publication model. At least I don't have a great benefit in writing papers back to back. If I do one paper also, you need to consider three. So I don't see a greater benefit unless like there's personal satisfaction of discovering something. And also, computer language is just to take some portion. All the documentation getting GPS is
You can apply
at least Microsoft is still okay.
I mean, even every time we try to do something very it says one result out. And in most cases, one of the reviews always will be you need error bars. How many times
can always
But yeah, I think even in academia here as well, it's very hard to concrete pieces. We do have a set, at least in Geographic, we have a cluster people can use but it's very susceptible to, we don't charge it. That means that if a certain time, we are exceeding that time, they're liable to get out.
Yeah, so they choose the slide with some points, and when you get away from the points, the error bar gets bigger. So it's just the same thing. It seems like like methodology we used to. There is no goal for the same problem. But I don't know.
I don't know. Yeah.
Also otherwise, now I can
Of course, yeah.
So where did you graduate from?
That's it.
The one in Mysore.
Yeah. Yeah. Yeah.
Or master.
Masters, and then converted to industry, and now he posted masters.
You intend to stay here?
Probably, at least for a while. Thank you. All right, so I think we can now continue with the next part. We stopped at a point where we were discussing about the definitions of uncertainty. There's one thing that I did not mention at the time, which was a very common, if you just search online, a very common definition that you'll find is from a statistical perspective, specifically that entropy is uncertainty. Entropy of a distribution is uncertainty. Now, that is absolutely true. But when we come to the idea of deep learning, discussing it from the sources of uncertainty is probably better from instead of the statistical information theoretic point of view. And by sources, I mean these ideas of aleatoric and epistemic uncertainties. We need a differentiation between what uncertainty we get out of the model and what uncertainty we get out of the data. The Shannon entropy uncertainty is very much, we pass an image, let's say, through a neural network, we get the final logits, we take an entropy across either the logits or the probabilities, and we'll say that this particular output or computational aspect is the uncertainty. But looking at it directly from that perspective is not as informative for us as saying something like, oh, the model is uncertain. We need to, let's say, change the model. That is more important than, oh, the amount of data is insufficient. Let's increase or decrease the amount of data. So looking at it from sources of uncertainty is probably more important for us in deep learning than looking at just a distribution from a single image's output. So that is something I probably should have mentioned at the beginning when we started discussing about uncertainty in deep learning models. All right, so I think right now it is 4, so that was a much needed break, at least from my voice. Hope everybody had a good break as well. So now let's talk about the next aspect of uncertainty, which is the quantification of uncertainty. Probably the best way of quantifying or understanding uncertainty is the idea of ensembles. In other words, we train multiple neural networks from different seeds, let's say from different initial starting points. We can train multiple neural networks. Now, we all know that neural networks are not convex functions. They have multiple minima that we can get very, very similar performances. Let's say you had a 95% accuracy in F1 of theta, you can get 95.1% in F2, and you get 94.9%. And yet, if you look at the parameters themselves, all of them are going to be very, very, very different from each other. So this is where this kind of an uncertainty comes from. But when you look at the outputs, they'll be very close together. And the difference between these outputs when I train n different networks is the uncertainty in that particular prediction. So this is the simplest way of computing and probably the best way there is of computing uncertainty. But again, this requires multiple trained models, not something that we can do at inference, right? At inference, we have a very specific criterion, which is that given a certain single data point in a single network, we need an uncertainty estimation out of it. Now, ensemble is probably the best way, but not something that is applicable to most people. And this is where we start thinking of how do we approximate this uncertainty. Good paper back in, I think this was 2020, was basically taking a small portion of the initial training data, considering that, and building some kind of priors on top of that. Or you can think of it as we hold out a particular validation set, and on top of that, we construct a this kind of a manifold. Again, let's say you have 1 billion data points to start with in your training set. You just hold out about 10,000 of these data points and then use that as some kind of a distance measure during inference. So you take your cat image, which let's consider to be a novel data, pass it through a neural network. You get a certain output probability distribution. Take the 10,000 images that you have held out in validation and find some kind of a measure between this validation data and your novel data. And that measurement can be your uncertainty. Now, of course, this does not require multiple networks, but it does require an additional amount of data or an additional amount of validation set within your uncertainty framework. This is, of course, much better than ensembles, but it still requires this additional aspect. And it's still not there yet in terms of the best kind of approximation. The next Another important milestone in terms of uncertainty estimation is this idea of Monte Carlo dropout, MC dropout. What happens is that you probably have all heard of dropout during training. So while training, a very, very important regularization method is that we, let's say, remove certain weights during the training portion. I only keep about 90% of the weights and remove 10% of the weights in the first epoch randomly. In the second epoch, I randomly again choose 10% of my weights, remove them. In other words, I'm just making them zero, or the embeddings activations within them zero, making sure that whatever effect that the weights are having, the 10% of the weights are having, they don't have an effect in that particular epoch. So essentially, we are regularizing the network, saying that if you did not have access to these 10% randomly in epoch number 72, can you give me a good prediction? And if you have another set of 10% that are not part of epoch number 73, can you still give me a good prediction? So this is what we usually do in dropout during training. But what if you do it while testing as well? So let's say I have a trained neural network, I pass a cat image with 10% of my weights canceled out, or let's say dropped out. I get a certain number of logits or the outputs from the final fully connected layer. Now I do n such forward passes, let's say 10 such forward passes, by removing 10% of the weights randomly every single time, which gives me 10 separate outputs or 10 separate logits all the time. Now we can do some kind of an estimation on these n logits in order to find what the uncertainty is. Again, if you go back to the ensemble, the idea is that given different weights, I'm able to pass in the same image and get slightly different outputs every single time. We are trying to mimic that with this kind of dropout uncertainty estimation, where we are just removing 10% of the weights each time. So the first time it was removed, you can consider that to be F1 of theta. The second time you remove 10%, it could be an F2 of theta. Third time, F3 of theta. So technically, you're constructing new neural networks at the test time in order to construct these n different logits. And you can basically construct some kind of a statistic on top of that. Usually these statistics are based on entropy of expectation of predictions and expectation of individual entropy of predictions. So that's a lot. So let me just talk about the first one here, entropy of expectation of predictions. So if I go back, if this was not dropout, if this was a single network that is giving me a single answer, this would be just this top blue part is going to be the logits that we get out of it. We put a softmax layer on top of it and we get the prediction, right? But now we have access to this n cross 10. 10 is because I'm considering some kind of a forward pass, number of forward passes. So I'm getting these kind of a matrix value. If I take a mean across this column and then take entropy across it, this is basically entropy of expectation of your predictions. So this is some kind of a predictive uncertainty that I can obtain from my outputs. Same thing, if I take expectation of individual entropy of predictions. So if I go back here, each of these rectangular blocks, I can put a softmax and get a, or I don't even need a softmax. I can just take the maximum and I get a prediction, right? Or I can do some kind of a statistic on top of them. I can do entropy on each block, get a number. Entropy on the second block, get a number. Entropy on the last block, get a number. And if I do this, and take an expectation across all of them, that is basically your aleatoric uncertainty. Now think about why that is the case. Every single block here, let's say, was a uniform distribution. That is, cat is 10%, dog is 10%, and so on. The network is not telling you anything. It could be a garbage network, and you don't even need a trained model in this particular scenario. The outputs in this particular case is nothing more than feeding noise into it. So if your data was completely noise, you would still get that high entropy per every single forward pass. And take an expectation of all this noise, nothing. It's still noise, essentially. So your aleatoric is uncertainty, which is the data uncertainty that exists with the amount of noise that can exist, which is technically associated with the measurement problem that we discussed before. Either there is some inherent noise in the data, or there is a problem within the measurement itself. That is reflected within the second term over here, which is expectation of individual entropy of predictions. Sorry, the first one is a little bit more straightforward, which is given some kind of a predictive uncertainty. So if I go back here, given some kind of statistic that I can get across all these things, let's say either variance or an expectation, then I just take an entropy across that in order to get the output, which is my uncertainty estimation. Now, there's a lot more theory that goes into why epistemic is predictive minus this aleatoric. It's easier if we have it in the opposite direction. Predictive uncertainty is a combination of epistemic and aleatoric. That is, the total uncertainty that we get from my output is always dependent on two things, which is the problem I have with my data and the problem I have with my model. Both of them combine together in order to give you this kind of a predictive uncertainty. It's easier if you take the right-hand term and put it on the left hand, and it's U aleatoric plus epistemic as you predictive. That is probably more intuitive, actually. Now, if you've worked with MC dropout, you know that yes, question? So that's a very good question. And I was about to say, as your embedding space increases, it is more difficult to say how Monte Carlo dropout works, because there's two parameters here, which is very much data dependent. One is that 10% thing that I mentioned before, which is that if I use 0.1 as my dropout, it might work for, let's say, very well-trained neural networks, but it's not going to work as well actually, it's the opposite. If I use 0.1, it's going to work very well with kind of okay-ish networks, but if I use 0.4, 0.5, it is very bad. But for a very well-trained neural network, I can still use 0.4, 0.5 and still get a good result. This is a very well-known problem if you're using something like transformers versus AlexNet. You can try this out. On AlexNet, your MC dropout is not going to give you a good result, versus something like on MVIT or some kind of a transformer, your dropout is going to give you a very good result. Reason being that the initial network is so good to begin with in your transformer that even if you remove 10% of your embedding space, doesn't matter. You still have a very, very good network to begin with. So in that case, you need to increase the dropout, and after a certain amount, you're just getting garbage outputs out of it, right? So it's very much dependent on the kind of network you have and the data and application. So for classification, yes, but when you're looking at something like segmentation, for instance, pixel-wise, you need to take this kind of a pixel-wise uncertainty estimation. The amount of embedding space that you're going to have in that particular case, the changes that you can do is, again, a lot. So in classes, it's more easier to obtain these kind of predictions and changes, but pixel-wise embeddings is going to be very, very, very difficult for getting the results. So Monte Carlo dropout has its own advantages, being that it's very fast and we can get some kind of good results out of it. But based on the fact how good, sorry? It is slower to train, but it is easier than a Bayesian method, for instance, because in Bayesian methods, you explicitly say that my weight has some normal distribution. But the only difference while you're doing Monte Carlo dropout training is that you would have had that 0.8, 0.9 in the beginning phase itself. Your weights would have taken that into consideration. And in a way, that regularization usually helps. In most cases, we use dropout in training. It really helps in the output performance. It creates a more robust model in general. So the dichotomy between the two, I think I would favor more towards using dropout, even though it might increase the compute resources, because of the fact that it would definitely be more regularized and robust. Yes. So you can do that, but the kind of assumptions that you're making is going to be very different. So let's say this is where the kind of error comes into picture. So let's say you have, like in the very beginning of the presentation, I showed a normal cat versus an animated cat. So the difference here is not the fact that the eyes between the two are probably the same distance away. The distance between nose and the eyes is the same distance. Doesn't matter if it's an animated cat versus a real cat, but the features that describe the eyes are very different. So the higher layers, the semantic features are not going to change as much. The lower layers will change more. So if you want a good regularization, you would rather have it in the lower, these kind of layers. But again, it depends on the kind of network. Usually when we are talking about CNNs, we usually want more dropout layers, so the later layers rather than the lower. So it's also dependent, very much dependent on the network as well. Depends on the kind of errors we are looking for and the network we are going to be using. Yes. I mean, so I wouldn't say it's, in fact, it's in terms of performance, it's probably the best one. So whenever you read papers, that is what we compare against. We want to get as close to ensembles as possible. So in terms of performance, it's the best. The issue is that we would have to train N different models, 10 to 50 different models during training itself, which is it's very problematic. And from a deployment perspective as well, that means that you have 50 models that are running all the time, which could be very problematic in this one. So it's the best in terms of performance, but worst in terms of the deployment aspect. So yeah. All right. So another method we'll so again. Monte Carlo dropout is definitely good, but there are parameters where it works and where it does not work. So we'll discuss going through the theme of the presentation, which is the idea of gradients. We'll be using that in this particular case itself. How do we estimate some kind of uncertainty estimate based on the gradient aspect? Again, gradient also has its problems and advantages and disadvantages. Like when we talked about introspective learning, as soon as you have a very high probability, like let's say 90% accuracy, it really doesn't help. Introspection is not going to give you like 95% accuracy. And if your results are something like 5%, right, in initial sensing network itself, you can't really, gradients don't give you much there because they're basically, you've not learned anything. Your gradients don't have as much information within their framework. So everything has its advantages and disadvantages. So does Monte Carlo dropout and gradient methods. But in this case, let's start discussing about this idea of gradient as single pass uncertainty quantification. So the main principle, of course, is that gradients act as some kind of a distance measure. Again, I'm using the distance very, very loosely. In this high dimensional space, it's very hard to define what that metric space is going to be for us to actually say that it is distance or any kind of a geodesic distance, essentially. But we can think of it, at least from a motivational perspective, as some kind of a distance measure. So this was a work last year, just trying to understand the purview of what neural network is going to be and some kind of a gradient analysis that was based on it. So again, the principle is that gradients provide a distance measure between a learned representation space and its, in case of discriminative tasks, some prediction or some new data in terms of generative tasks. If we think about training, we use this a lot, this idea that we have some kind of a manifold and we have either a new data distribution or a single data point from a different data distribution. We use gradients a lot in order to mold our representation space, our weights, to encompass the new gradient space itself, right? But we need access to something called L, which is our loss function. And we don't have access to that loss function in this particular case. Very similar to what we were talking about before. We have some kind of we need to construct some kind of a pseudo loss function that tells us what this changes so that we can backpropagate and get some kind of gradient. And of course, we have done this before in introspective learning, which is we backpropagate different contrast classes. We can backpropagate contrast class 1, we can backpropagate contrast class 2, and so on. That essentially means that we are saying that the new data point that is coming in belongs to a separate cluster, either Q1 or Q2. neither of them are correct, or one of them may be incorrect or not. Basically, we have no idea which class this data point belongs to, but it's perfectly fine. What we are interested in is how the gradient changes based on these classes. So we backpropagate all contrast classes. And the main principle, of course, is that higher the distance, higher the uncertainty score. This goes back to one of the motivating examples where, given a certain domain, if we have a lot of data points in that domain, then our output need not have any uncertainty. But as soon as it moves away, we don't know if it's a sinusoid, there's a larger region of uncertainty that exists. So if we are going away from the trained manifold, that basically means that the uncertainty is more. A very simple and straightforward principle, and we are measuring that using this kind of uncertainty. So the classes where it's going away, too far away from the training distribution, is the one which will have a this kind of a higher uncertainty score. If I were to go back to this kind of a toy manifold example that we had started off with, we have this X that is on top of the representation space. You have a very small region around it. That region is telling you what kind of a local information is possible. Based on that, now we are discussing, okay, maybe this hump that is there, this red hump, I'm telling the network that you are incorrect. I'm erroneously telling that network that you're incorrect. Put some other kind of a class. Let's take you and make you as X dash. I'll put either contrast class Q1, let's say, and you have to move across this region. If I say that you need to put contrast class Q2, then you need to move a higher distance away from the region, the hump that you already had before, right? So what we are changing right now, instead of just looking at the local information around the embedding that we have, we are making this kind of an intervention and saying that this data point is somewhere else. It shouldn't be here. It has to be somewhere else. And we are trying to shift the manifold and see how much shift is required in order to take this into consideration. And that is where the uncertainty aspect is coming from. So again, explainability, we are multiplying activations with gradients. So basically, we are still staying within this kind of a manifold itself. Now we are moving away from activation. And just to recollect, when I say activations multiplied by gradients, I mean the grad thing. So if you remember, we had this alpha parameter where we are aggregating all the gradients and multiplying that with the last convolution layer, right? So that multiplication was around the activation, which is essentially the embedding. Now we are moving away from the activation and saying that the gradients are the main features. It has to be like far away from the network space itself. So that is the kind of difference that we are discussing between what we talked about before versus what we are talking right now. So we need some kind of statistics of these gradients essentially. And what I'll be talking about is a very, very simple statistic, which is this energy or an L2 distance, L2 norm that we can get out of it. Again, this is a slide we had talked about before. Given some kind of network, we take the original input data, no corruption or no out of distribution, no novel data, just training data. We can get some kind of gradients out of it by backpropagating a vector of all ones. Again, the theory of that is a little bit more complicated. And based on these gradients, we can get some kind of statistics. And we are showing these statistics here. Let me try to, all right. So we have two data sets. We start with MNIST data set and LSUN data set. MNIST data set is the one in blue. LSUN data set is the one in orange. MNIST is the training data set. LSUN is the testing data set. In other words, we have something called an out of distribution during inference. We have only trained on these number images on MNIST, but while training, we have a completely new data set, which is LSUN. So now we need to ask ourselves how the network sees these things. Let me first describe the graph that you're seeing here. The x-axis is essentially the different layers. Let's see if I can. So layer 0, batch norm 1 bias, layer 3, 0, batch norm 1 weight. Essentially, all of these are layers. I believe this is either ResNet 18 or VGG 16. But based on this particular architecture, we can take the training distribution or MNIST dataset, the test set from MNIST, forward propagate it, and backward propagate all the contrast classes, ones, all the ones, and we can back propagate all ones, and we can just take an L2 norm across different classes, across different layers. So dou theta naught, j theta naught, x, y, c. 0 is the layer, and n here is the nth layer, basically. So if we had something like resonant 18, 18 different layers, I believe VGG 16 has like 29 at the very end, but you'll have that 29 n at the very end over here, which implies that every single layer can have a certain L2 distance or L2 norm associated with it. And what you're seeing is that when I backpropagate for MNIST, that is blue. When I backpropagate for LSUN, that is in orange. Now, there is very clearly a difference. Y-axis is showcasing that L2 norm, that energy, essentially. There is very clearly a difference between between layers, essentially, where there is a difference between when I'm backpropagating something like LSUN versus MNIST. You can see at the very end, it's not as visible. There's more kind of combination, because again, the reason being that at the end of a network, it's more semantic features. It has already learned everything it needs to, and it's just combining all these features. The problem happens in the initial layers where it has no clue how to treat something from LSUN. All it has learned is like these circles for zeros, straight lines for ones, and so on. So you have much, much more richer representation in LSUN, right? So a network has no clue how to make use of these features, essentially. So you have this wide disparity between the initial layers. You see that until the I would say until the mid region, and after that, it becomes a little bit more difficult to see the difference within these things. But ideally, the goal is to showcase this difference, that there is a difference between in distribution data versus something which is out of distribution. Okay. So if we were to do this against other data sets as well, for instance, in this case, MNIST versus SVHN, Tiny ImageNet, LSUN, Cypher10. So in the previous case, I was showing layer by layer, but let's say I'm just going to average across different layers without considering the fact that initially and later on it's going to be different. Because again, if we change the kind of data set we are using, if I were using Tiny ImageNet as in distribution, then initial layers wouldn't have shown any difference, because an ImageNet network that is trained on an ImageNet has learned all features initially. It just doesn't know how to combine them at the very end, right? So it would have been in the opposite direction. So I'm not making an assertion saying one is better than the other. I'm just saying that if you just combine all layers down the line, usually your in-distribution data set is going to have a much, much lower energy as compared to all the other data sets that you see on the right-hand side over here. And you can use this as some kind of an uncertainty measure to construct either some kind of a classifier, or you can take some statistic out of it, either create a threshold and use that for some kind of detection mechanisms. So the next few slides, so you can also do this not just for out of distribution detection, but for something like adversarial detection as well. Now, if you're not familiar with adversarial detection, this is this kind of an engineered noise that we can apply on top of existing data. So this Panda, if I were to show this to a neural network, it would be with a 57% confidence, the network would classify it as a Panda. But then I'm going to engineer a noise which is imperceptible to humans. This, of course, has been multiplied by a lot so that it is visible to us. But once you add this noise, this is how the Panda is going to look like on the right-hand side, right? In this case, the network is going to classify it as a given with 99% accuracy, which again, Panda was 57, which was the right answer, but then a given is now 99% accuracy. So this is not something that we want out of a neural network, and this is basically what an adversarial image is. Ideally, when we discuss robustness, we want to make sure that anything that is out of distribution or anything that is adversarial is also recognized, or it's detected as something that is adversarial, right? So this idea of using gradients is very useful when it comes to both adversarial and out of distribution detection as well. So against different attacks, you can have multiple methods, and usually the Rs here was actually from the gradient perspective. It usually does quite well in terms of detecting if something is adversarial or not. So next few slides are about this, the out of distribution detection. Essentially, the goal is either some kind of corruption. Like, let's say I've trained my network with just Cypher10, but then I corrupt it with these kind of 19 different distortions. So the goal is to make sure that you find what these corruptions are, or you detect that the corruptions exist within the image, rather than just classifying it and saying this is a image of a bird or some other class. So, I mean, there are numbers. The upshot of it is that usually gradients do well. One thing I want to bring attention to is that usually it's very easy. So the level 1, 2, 3, 4, 5 is when we have progressively increasing distortions. So when your distortion is very high, it's very easy to say that if it is distorted or not. But what you should really concentrate on more is the level 1 and 2. Even for humans, it's not very clear when something is distorted with these kind of low distortions. So for a network to say with high accuracy that, okay, this is a corrupted input, don't do anything with this input. Just pass it on along, or just inform the human being outside that this particular image is corrupted. It's very important to do it in the level 1 and level 2. So generally, when you're reading these kind of OD detection papers, it's more important to look at the lower corruption results than look at the higher corruption results, because usually it's very good in the higher corruption scenarios. Same thing with the kind of data sets as well. Like usually the pure TSR, which is more realistic kind of distortions, it's a little bit more harder to do. So for instance, the gradient-based methods don't do very well in these kind of distortions in the higher layers, but they do quite well when we do, again, from the level 1 and level 2 distortion types. So that was about corruption detection, and out of distribution, again, is a very simple concept. The same concept, sorry. You have, let's say, training distribution as MNIST or some data set. While testing, you just test it with different data sets. In this case, it could be SVHN, it could be Cypher10, Tiny ImageNet, and LSUN. And in all these cases, these kind of gradient-based methods do well. So given Cypher10 as in distribution, let's say I'm using different data sets as out of distribution, SVHN, Tiny ImageNet, LSUN, we are able to, the gradient-based methods are able to do well across these different classes. So again, I'm not going to go deep into the numbers itself. The numbers generally suggest that gradients do well, but it's also very important to note that where you're looking at in terms of numbers is probably even more important. The type of corruptions you're looking at is also even more important. That kind of an analysis can be very, very useful. So just to summarize what we have done in terms of parts 1, 2, and 3. So we started off by saying that in practice, we have no access to any kind of data. The training manifolds that we had access to during training is ideally what we want. We want the entire manifold to be understood by us. This, of course, is a very mathematical interpretation, but it's not possible in empirical neural networks. And furthermore, we have no access to training data during inference. So this is essentially how what we are left with during inference and in practice. But we have talked about the fact that even a novel data point, when it embeds itself on a neural network parameters, we get some local information out of it. And by using gradients and moving across these, traversing across this manifold, we are able to get more local information by looking at these contrast classes, by saying that these contrast classes are in fact correct. We get the difference between the, let's say, a flamingo and spoonbill, and that difference is located in this green region, let's say. Right? So the difference in features or the loss in features is something that we'll have access to during inference, even though we don't have access to those new images during testing. So that was part 3, which was we'll come back to the idea of uncertainty, essentially, even in this aspect, intervenability. Yeah. I think you're talking about EGL, which is expected gradient length. So expected gradient length does something very similar, which is you take the gradient, you take the some kind of energy across different aspects, and you'll be able to get some measure of that. The difference here is in which kind of layer we are looking at and what that means from a neural network perspective. So I think that method is specifically called EGL, expected gradient length. Grad norm as well. Yes, so this was the 2020 paper that exists. So grad norm has the opposite. Can I go back to? Yes. So grad norm has the opposite conclusion, where by backpropagating all once, we need to look at the final layer, and the gradients from the final layer of in distribution is going to be, I believe, greater than the out of distribution. So here it's the opposite. Gradients of out of distribution are much greater than in distribution. So that makes sense if you're looking at the final layers. Grad norm. So grad norm specifically does it for the final layer. But there are two confounding factors. One is if you look at different layers, then in the initial layers, it's the opposite phenomenon is seen, where the out of distribution is in fact more. And second one is the kind of data sets we use as well. So if you're using MNIST data set versus something like ImageNet. So it's not all, so grad norm is not always clear in terms of when those assumptions hold or the opposite assumptions can occur. But grad norm also does the same thing, out of distribution detection, corruption detection, all these things. Yes. Sure. I think temperature scaling is probably the best and the easiest way of doing what you're saying. Though one thing I'll say is that calibration is not always the same as uncertainty. The idea, so calibration can be part of uncertainty, but if you actually take a look at MSE loss function, there's a decomposition that you can do, and you can get three different terminologies. One is the calibration aspect, another is called the sharpness aspect, and the last one is the uncertainty aspect. So uncertainty in some respect is something that can be completely independent of calibration, more from a statistical theoretical point of view. But in many cases, it kind of coincides with it or correlates with it, but it's not the same. But if you're specifically looking for calibration, I think temperature scaling is probably the easiest thing that you should try, and it generally works. All right, so the next part of the talk is going to be about the idea of intervenability. Many of the things that we discussed with explainability, uncertainty, we'll bring it back in this concept of intervenability. In many ways, intervenability is a very general topic. There's no single way that I could define what intervenability is, so I'm not going to try. The next few slides, next 5 slides specifically, will talk about 5 different definitions of what we mean by interventions in neural networks. Now, for instance, if you've heard the word intervention, it most probably is going to be in a context of something called causality. The idea is that we want to have some causal analysis of the world around us. So when we were talking about explainability, I made it a specific point to say that these are correlations and not causations. The reason being that it's what a network thinks that is important for making the decision, but it is not the reason that it is actually something. And the reason that it is something is what we would call a causality, right? So if I were to give a very general definition of intervenability, then I'll say the amenability of neural network decisions to human interventions. I would say that would be what we would call as intervenability. But if I were looking at it through a causal glass, then interventions in data are manipulations that are designed to test for causal factors. In other words, if I'll make a very definite statement saying that a straight beak is what makes a spoonbill, that is something that you should now question me and say, okay, maybe I'm going to add a slight bulge to the very end? Is it still going to be a spoon bill? And this is what essentially interventions are. You make that small change and ask yourself, okay, is it a causal factor or is it not a causal factor? You take that spoon, you take that bill and then put it onto an elephant, because the only thing I told you is that if a beak is straight, then that means it's a spoon bill. So a straight beak on an elephant, does that make it a spoon bill? Right? These are the questions that you need to ask me when I make some kind of such a definitive statement. So those are the kind of interventions you're doing on my statement in order to test for the causal analysis of my statement. So that is the kind of intervention from a causal analysis perspective. Another definition of intervenability can be from a privacy perspective. So if you're familiar with the concept of, this concept of machine unlearning, let's say, I think it came out in 2016, I believe. So machine unlearning is where once a neural network has been completely trained, let's say it was trained on medical data, and one of the patients comes back and says, hey, I don't want my information out there. Please remove it from all the knowledge bases. You can easily take that out from the data set, but you want to take out the information that has been learned from a neural network out of that particular neural network. So technically, you're machine unlearning from a trained neural network, right? So in other words, you're intervening on top of a trained neural network to remove that knowledge. So this is a kind of technical intervention that we are trying to do in order to have a good privacy, in order to make sure that the needs of the person who wants their data removed is done. So this is an intervention from a privacy perspective. There's also an interpretation perspective. We'll talk a lot about this. So whenever so the first part of this talk was all dedicated towards explainability, but I did not spend any time talking about the evaluation of these explanations. The reason being that we'll discuss them here in this part, which is any time that I want to evaluate my explanations, I need to intervene within my data in order to show it to the neural networks again, which comes under this aspect of intervenability. The next one is the idea of prompting. So I'm just going to be talking about visual prompting in this particular case, but you're probably all familiar with the idea of foundation models and how these foundation models can take multimodal data or some inputs from human beings, right? So visual prompting is one such thing. If you're aware of something called SAM, which is segment anything model, you can take segment anything model and human beings can actually go through and prompt on this network, and it will segment the things that you have prompted on. So it's the network is taking the data and then it's taking the human prompts. I will prompt in a different way, you'll prompt in a different way, but it'll still require, but probably within the same object. So it'll still need to give you that particular object as a segmentation. So there is this kind of intervention that happens within these foundation models, and that is where prompting comes into picture. The next one is benchmarking, and this is, again, the last definition of intervenability. We talked about robustness quite a bit. And one of those things that we discussed was about these data sets, Cure data sets, CIFAR-10C data sets, ImageNet-C. All these data sets, what they do is they intervene on top of the data. They basically add noise, corruptions, out of distribution, and everything on top of the data. And then you're able to now evaluate for the robustness, the sensitivity of the data sets that can exist. So in all these models, interventions are essentially trying to benchmark your data and say how good your network is or is not. So in many ways, this concept, this idea of intervenability is about trying to interact with the model that has been learned. And based on this interaction, can I get something out of the network? Can I have a mathematical model for what this interaction is going to look like? Can I help a certain application, either evaluate a certain application? So all this comes under the general umbrella of intervenability. Now, everything I've told until this point makes it sound like intervenability is like a very positive thing. And in most cases, that is true. Intervenability is a very positive aspect because it allows a human being to interact with the neural network and understand the neural network. And that is essentially what we want, right? If you're looking at some LLMs and ChatGPT chatbots, for instance, you're expecting human beings to go through and work with these LLMs, and you want to understand what their operation limits are. The human beings or the users need to understand these operation limits. But there are instances where interventions can be negative. So I'll take the next 2-3 slides to just talk about these ideas of negative interventions, just to set the stage, to tell you that, you know, intervenability is nice and all, but we do have bad actors. And because of that, interventions are not always good. So for instance, something like repeated interventions can happen at inference. This idea of membership inference attacks. So if you're not aware, you can, let's say I have some machine learning as a service model from Google or Amazon or something like that. And you have infinite access to this model. You have infinite data that you can pass through the model. You can get certain outputs, and you can use those outputs in order to say if a given data point was part of the training set. Now, think about it from a medical health perspective. You have trained on a large amount of health data, electronic medical records, health records, for instance. You don't want the training data set to become public. But using these kind of membership inference attacks, you can recreate or re-synthesize the data, some, again, very private data like medical records, and you can put it out in the open, essentially, which is not good. Again, this is possible because we can have these kind of repeated interventions that occur within a neural network. Of course, there could be some kind of engineered interventions as well. And we already talked about adversarial attacks, where I can add a small amount of imperceptible noise to my data point, my image, and the output that I'm going to get is very, very different from what it was supposed to be earlier. So this is a kind of an engineered intervention. My favorite is more of a trial and error intervention, because this is what generally happens with human beings. So this was a new data set where, let me go. So we talked about the SAM model, right? Segment anything model before. Human beings have actually gone through and try to label something. In this case, this is a baseball bat. Someone has at B, basically. So at a time instant B, someone has finished their labeling, saw that their output looks something like this. They were shown a mean intersection over union against the ground truth, and they saw that it was like 0.8. So they wanted to make it better. So they went through and added an exclusion point here. So if you don't know what that means, so in prompting, we have two things, which is inclusion and exclusion points in segment anything model. If something is green, which you see here, then that means that you're interested in that object. If some point is red, then that means that you're not interested in that object. So green points are inclusion points. You want your object to have these kind of inclusion points, and red points are exclusion points. Now, it makes perfect sense. This is correct. This should be an exclusion point, right? But Sam looks at this and thinks that, oh, this is white in color. This region is also white in color. So probably this person want this part to be excluded as well, right? In other words, this segmentation here was correct. But then because you added this kind of exclusion point outside, the color of this being white and white here means that Sam now considers this portion to be incorrect, and it changes the segmentation. So why are this trial and error? A human being who has no knowledge about the operational limits or understanding of what these foundation models are, when they use it, it's very hard to basically either teach them or try to understand what they do, essentially. So that is what we see here as well. So that is what we see here as well. So in this case, IOU, which is the intersection over union between SAM segmentation and the ground truth mask, at B was very high because it was pretty good. But then people, this person went and put an exclusion point, and you see it becomes worse. And this person again removed that and added exclusion points elsewhere, it becomes even worse. So more you're trying to overprompt something and make something good, it becomes worse and worse. The reason being that human beings, these annotators, they don't understand the operational limits of these models. And because of that, the interventions that they do is probably going to be incorrect. And worse is the case that Sam also comes with this score. It gives you a score, what it thinks should be the intersection over union. You see that it's exact opposite of the true case in this. So it thinks that as soon as someone puts an exclusion point, it becomes confident that its results are better than it was before. And you can see that it's going in the opposite direction. It's becoming more and more confident, while the IOU intersection over union actually becomes worse and worse. So this is the kind of trial and error interventions that can happen in visual prompting. We don't really understand these models, but still we have them out in the open for people to actually go through and use, right? And this causes issues, real issues. So again, these are the kind of negative interventions that can happen within this framework. All right, so that is about the definitions of intervenability. Again, it was a very broad definition, but the simple question that intervenability is trying to answer is that how amenable is a neural network to human interactions or interventions? And generally, these shouldn't be expert humans. It shouldn't be like an ornithologist. It could be like a kid when we were talking about the explanations, right? Someone who has no knowledge, but still is trying to interact with these kind of things. So you want some kind of a mathematical framework to understand these interventions. Again, whenever we think about interventions, the first thing at least that comes to my mind is causality. And that is how, and in the beginning, I thought, okay, this is how we need to understand these interventions based on causality. So let me just go through trying to see how causality works in this kind of a framework. So we have something called causal inference. If you're not aware, the idea is that given a certain data set and given a certain model, we can make small changes or interventions, very, very restricted changes or interventions within these kind of models, which let's call it structured causal models, and within the data points itself in order to find what the causal factors are. So I started by saying if I put a beak onto an elephant, right? It was an actual example that I have in the slides. I just talked about it before. So let's say that I am giving you this kind of an example and telling you that this beak is what makes a spoonbill. The straight, flat beak is what makes a spoonbill, which means that if I were to delete this beak from this image, it would no longer be a spoonbill. So that's the practical outcome of that statement. It also means that if I were to take this beak and put it on top of an elephant, you would no longer recognize it as an elephant. It would just be a spoonbill in this case, because I'm making that causal statement. I'm saying that the causal factor for a spoonbill is this beak. Again, it is incorrect, but that is a causal factor that I am trying to assert if it's causal or if it's not causal, right? So we fix a causal feature, a feature that is being tested for causality in the data, in this case, beak, and we then go through and try to find the causal factors. Now, what is the problem when we are discussing this? Again, there are 3 steps or 3 rules to saying if something is causal or not. We are still in step 1. But even in step 1, we now have a problem. There are no causal features. I can't just say where the pixels of this beak begins, where it stops, and which part is the actual beak, where the beak starts, where it ends. It's very hard to make this assertion. The network is also like a 1.76 trillion parameter model. It's not a structured causal model where you have specific weights, nodes that I can go through and make it 0, right? It's the number of parameters is insanely high. How can I go through every single part of the model and then switch it on and off in order to test for causality? So it is not, it's impractical essentially. The next rule within causal analysis is basically going through and trying to determine if what I said was true or not. So let's say I delete a different part of the image. I'm taking a certain action. I'm deleting the feathers that was there before. Ideally, even without the feathers, the network must still say that this is a spoonbill just because of the fact that the bill exists here. And on the right-hand side as well, I'm adding these other I'm not sure what you call legs, hoofs, I don't know, the lower part of the bird essentially. And it should still say it's a spoonbill because of the existence of this beak over here, right? Again, we still have the same issue that we had before. You could create a generative model, and these days generative models are very good, where you have an elephant with this kind of a beak, but you still have to pass this elephant with beak through the model, and the model has never seen that before. It's not in its training data. It's a completely novel data. Any output that you get out of it has a huge amount of uncertainty, and it probably is an incorrect answer, right? So you're left with so many questions right now. Is the data I have correct? when I pass this data point through the model, is the output that I'm getting, is it something that I can actually use? And the answer is generally no. Of course, there's a rule 3 as well, but at this point, I think we're just beating a dead horse, which is that causal analysis is very, very hard to attempt on these kind of large scale models. You need to have a specific kind of structured causal models, and you need to know, it's possible, of course, on like tabular data sets, where it's easier to have the specific features for you. But as soon as we come to these larger visual models, it's very, very hard to say if something is causal or not. And whenever we talk about these interventions, that basically means that the interventions are going to be incomplete, right? So causal models are fine if you can go through all possible interventions. That is, you change 1 pixel, you change 2 pixels, you change 2 pixels, one apart, and so on. But you'll never be able to do something like this. But we use this methodology in order to create explanations. RISE is a very common method that we can use. So whenever we talk about GradCam and stuff like that, we need access to the models themselves in order to create the explanations. RISE, on the other hand, is a black box model. So you don't need access to the model parameters to create these explanations. What you do is you create 6,000 such random masks that you see on the left-hand side here, which is M. You create these 6,000 random masks, multiply it pixel-wise with the original image. And you can probably see that here. Let me go zoom in a little bit. Yes, so this is the multiplied or the masked image. You pass that through the black box, which is your neural network, and you get certain outputs, right? So 0.09 is essentially for class 1, 0.74 is for class 2, and so on. What you would do is multiply this 0.09 with the first mask, 0.74 with the second mask. And when you do something like that, you usually get a good explanation, a representation. And this is what is called RISE, explainability technique. So again, instead of causal deletion, it's similar to that masking deletion part. RISE deletes randomly. There's a very simple change that we can make to RISE to get a very different kind of a result. So in previous RISE, this is important. You're multiplying the probability with the masks. Let's say I'm not multiplying the probability with the masks, but I'm multiplying the change in probability with the mask. So I have these randomly generated 6,000 masks. I have the multiplication with them. I pass it through the network. I get some result, right? Now, I pass the original image through the network. I get some probability, let's say Fi. I pass the masked image, I get Fi dot n. I subtract the two things. Again, this is the difference. Before, I was just multiplying with the mask. Now I'm subtracting the mask and multiplying with the opposite because it's a negative here, minus Fi dot n, right? And I get a very, very bad explanation. Again, this is my, as one of you had pointed out before, this is my interpretation, my subjective interpretation. This is a very bad mask compared to the previous one. It would have been well and good, except that existing evaluation metrics, if you look at the actual numbers, this is a much better mask than the one that RISE produces. So because we don't understand all possible interventions, we are just doing 6,000 instead of all possible interventions, and we have this incomplete interventions. Our explanations that are going to be generated, even though objectively they are excellent, they give you much better numbers, subjectively they can be extremely bad. And this is a big problem with an explainability research. Whenever we try to evaluate explanations, we make these assumptions about causality where we can do these kind of evaluations which are inherently incorrect, and it's very, very hard, and small minor tweaks can lead to very large changes. So again, if you remember, all we are doing is because we are trying to get some kind of a mathematical understanding framework. Is causal analysis good? Is causal analysis for interventions, for trying to understand interventions good? Probably not, because we'll never, in visual data at least, we'll never have a complete set of interventions. And what I'll be talking about today is that that's fine. We should accept it. We should accept that all interventions are impossible and calculate the uncertainty of residual interventions. So the idea is that, yes, we are going to have this kind of an explanation map, and that is fine. This is an explanation map that could have gone either way. Why is this particular pixel not part of the explanation, right? That is a question you can ask yourself. There is a residual this region here, which is not part of the explanation. And that's an important thing to discuss. And that is an important thing that my explanation is not showing. And the answer for that is saying that, okay, we have an explanation, but there is an uncertainty about this explanation, which we are showing you as well. And having both of these at the same time is probably a better analysis of this intervention. So in other words, uncertainty is a good framework for interventional analysis than something like causal analysis. I'll bring back this particular slide, but essentially the goal is to just showcase these two things together, which is that a good mathematical framework for analyzing some interventions is this uncertainty. Now, again, you know this as an explanation. You don't know why it's an intervention. And to do that, I need to motivate something. I need to motivate the idea of what explanatory evaluation is and talk about that a little bit before I come and talk about the method itself, about how to derive this kind of uncertainty. All right, so we'll start with the idea of motivating explanatory evaluation. So specifically, we'll talk from interpretability or explainability perspective. The detour for us is to understand the explanatory evaluation before we move on to talking about uncertainty framework. We'll talk about 3 ways of evaluating explanations. And spoiler alert, none of them are good. All of them have their own issues, and we'll talk about what those issues are. Generally, what happens when we talk about these kind of evaluation is masking. There is some kind of masking that we do on top of images in order to say whether a certain explanation is good or not. Let's talk about the first one, which is masking using explanation heat map. Let's say that I have access to 2 explanations. One is this was taken specifically from GradCam++ paper. So SX1, I believe, was GradCam explanation. SX2 was GradCam++ explanation. So what the authors did was they passed these images through the train model. So they took an image, they got the heat map, and they did a simple-wise masking, a pixel-wise multiplication or a masking. And once they got these 2 images, they passed it through the train model. For GradCam++, the image said that it is a spoonbill. The model said it's a spoonbill. Versus for GradCam, it's, let's say it says crane. So the claim now can be that once you give me the heat map, and I mask the image using that heat map, if I pass it through the network again, I get the same output as before, which is a spoonbill, right? So expectation of y given SX2, which is the image here, is going to be greater than expectation of y given SX1. SX2 and SX1 are these intervened images or masked images. So y given SX2 is always going to be greater than y given SX1, which makes complete sense. And intuitively, it is correct, right? Your network is still giving you the right answer, in spite of the fact that a large portion of the image has been masked in this methodology. So explanation 2 is better than explanation 1. One way of evaluating the 2. The problem here, of course, is that larger explanations imply more features in masked images are intact. So I can have an explanation which is, heat map is everywhere, and this kind of a evaluation technique is going to encourage such large explanations. The fine-grained nature of explanations are not going to be talked about in these kind of methodologies. So this increases the likelihood of a correct explanation prediction when your heat map is very large and it's able to give you a good trained model. So fine-grained explanations are not promoted. So the next technique that we'll see is pixel-wise masking using explanation as importance. Again, makes a lot of intuitive sense as before. Pixel-wise explanations basically tell you that given a certain heat map, the most red region here probably has the highest importance, right? That's why it's complete red, versus the blue here has the least importance. So instead of masking the entire image using the explanation, what you do is you mask the highest region first. So the most red region, you make it black or you make it gray or something like that, the mean basically of the network, and pass it through the network and see what the output is going to be. You when you see that the network prediction hasn't changed. Take the next highest, second highest importance map, you delete that and pass it through the network and repeat until all these pixels are deleted, essentially. All the red regions and the regions have been deleted. All the explainability paths have been deleted. You could do the opposite as well, insertion, but let's look at deletion first. As and when you remove the importance pixels, you see that your prediction, your probability basically goes on decreasing. So you started off by saying that this is a bit turn. At a certain point, when you have deleted 10% of all pixels, you're only about 20% confident that it is a bit turn compared to before when you were about 80% confidence, right? So in the first pixel itself, when you remove the first pixel, if the network says it's not a bit turn anymore, that basically implies that this is probably the best pixel for saying that this image is a bit turn, which means that this area under this curve has to be as less as possible. So technically, it makes a lot of sense. Again, from a motivation perspective, it makes a lot of sense, even in other things as well. If you're looking at fine-grained explanation, this kind of deletion, it encourages these fine-grained explanation. The exact opposite of that is something called a insertion game, where instead of deleting the highest pixel from the image, you start putting in the highest pixel, highest explanation pixel to like a gray mask. So if this particular pixel is important, then that means that just based on this one pixel, your image, your network must say that the image is that of a spoonbill in this particular case. And you do it stepwise. In the first step, you add 1, second step, you add 2, third step, you add 3, and so on. In doing something like this in the beginning, your output is going to be prediction probability 0 or 1 by 1000 if it's ImageNet. But as and when you add more and more pixels, your probability keeps on increasing, right? Hopefully, it happens very quickly. That means the most important pixels have been added to this gray canvas, and your area under the curve is going to be very large. So again, makes complete sense, this kind of an insertion and deletion. It's very well theoretically motivated from a causal perspective as well, motivation. But going back to the explanation I had before, this is rise explanation, this is shape explanation. If you look at the outputs here, if you look at the deletion game, shape has better results than rise. If you look at insertion game here, shape has higher AUC than rise. I believe rise is AUC 0.497, while shape is 0.72 something, right? So the reason being that pixel-wise is not how human beings see. None of us actually subjectively decide something based on pixels. In fact, we can't even perceptually make out pixels. I'm looking at faces right now, which have no pixels in my mind. It's basically a structure, right? So whenever we discuss these kind of evaluation metrics and we look at pixel-wise metrics, it is very, very, very hard to come up with a metric, essentially, that connects the pixel-wise perception to something that is, let's say, structure-wise or other kind of subjectively viable metrics. So even though this kind of progressive pixel-wise insertion and deletion makes a lot of sense, both from a motivational perspective and from the theoretical causal perspective, we have problems with it more from a subjective and perceptual perspective. It's not reliable at all. So the thing that I was talking about, which is rather they view scenes in a structure-wise fashion, let's put that to the test as well. So there are structure-wise ways of creating these explanatory evaluation metrics. So instead of doing pixel-wise, can we have some information encoding? So something like Huffman encoding, can we use that in order to create some kind of explanation? So in this particular case, let's say I have 3 different methods, causal cam, grad cam plus plus. So all these methods have to encode the most, the best information, the most discriminative amount of information. If they can encode the most discriminative amount of information, these particular heat maps, then they are good explanations. So that's like a simple way of saying that good explanations have more information or have better discriminative information within them. And we can do it similar to the pixel-wise insertion deletion that we were talking about earlier. But instead of pixel-wise, what we are doing is the structure-wise. So we take a particular threshold in the explanation, we kind of cut off at that particular threshold, and we use this Huffman encoding in order to calculate the amount of information, the bits essentially, that is being used on top of this information thing. And we do it progressively. So on the x-axis, you have a ratio of Huffman encoded masked and original images. Smaller the ratio, less is the number of bits encoding it. And y-axis is the performance. So what you see here is that ideally you want this to be highest performance with the least amount of, so the best information in the least amount of bits that is possible. So basically ideally you want it to be as left as possible, right? So this method, causal CAM, essentially is giving us a good approximation, or is giving us a good structure-wise information within the heat map thing. So this is deletion. We can do the exact same thing for insertion as well, where in this case, ideally, it must be towards the right as much as possible, where you're inserting it, and with the least amount of bits that is inserted, you want the most amount of information in a blank canvas. So ideally, you want to be on the right-hand side, which you see on the method here, essentially, which this is red, but since it's behind, you see it's more as a purple thing. But this is the one that is in causal CAM, which is in red. I don't think there is a good rationale for choosing Huffman encoding by itself. I think it's the most simplest and the most expected way of trying to encode something, or at least it was in the beginning, that is the way it was encoded. So it's probably more simplicity of the Huffman encoding, which leads to this kind of so we take a threshold. So we take a particular threshold and say that this is the only patch that is there. Everywhere else it's 0, so it's not adding any bits to the framework. So this is the only place where something exists, essentially. So that is where the more changes are, and we can get a number there. But the problem, again, I started off by saying that explanatory evaluation, there are many of them, but all of them have issues associated with them, right? So the problem with this evaluation metric is that it's really not thinking from a human perspective again. Sometimes what happens in these kind of data sets, the results, there's a yellow patch, let's say, on these kind of medical data sets or something else. These are prioritized. These are the ones that lead to the maximum amount of discrimination. So let's look at this things. The best explanations are if you take this particular image, this explanation here has 79% probability that the middle explanation in top row is good, which is basically where you need to check to see if there is COVID or not COVID. This was the data set for COVID-19, essentially. If the explanation at the bottom right, then the COVID probability rises to 91% if you pass this masked image through the network, right? So it's finding you the highest probability or the ones which have the most dense information, but it is not subjectively a good explanation at all. Same thing at the bottom as well. It's 90% probability in the middle one, 90% in the other one, but the place where it's looking at in terms of heat map is very, very different, right? So again, as I said, there are pros and cons we talked about 3 different methods. One is explanation heat map masking, pixel-wise insertion and deletion, and structure-wise insertion and deletion. There are pros and cons in each of them. None of them are perfect. Ideally, you can think of it as you can try multiple ones, or sometimes all of them give you the best results, but when you subjectively look at it, it's not something that you would expect is a good explanation at all. So this basically is almost like a challenge, which in the idea of intervenability and explainability. So any type of masking that we are doing on the data that you pass through the network is an intervention, technically, right? So choosing the type of this intervention, it's almost like a art right now. It's not a science where we know exactly what kind of intervention we want on the data to get a good output. There's no single best interventional evaluation strategy that exists. So again, going back to the original framework, the idea is that we want to have some kind of residual of this interventions, and that is given by uncertainty. So this is a case study in terms of utilizing what we talked about before, which is the contrastive explanations and the uncertainty, predictive uncertainty, and see how we can get something here. So let's say let's bring back the bull mastiff from last time. Let's ask the question, why bull mastiff? And we see this as an explanation. It's showcasing the face as we want it to. But our goal is to construct this map on the right-hand side as well, which is showcasing the uncertainty of the map. Now, the reason you would do something like this is that you're bringing a whole new evaluation setup into picture. I can use all the previously whatever I discussed before, which is the idea of ensembles, let's say Monte Carlo dropout. All of them can now be used within this evaluation framework for explainability, right? So that is a motivation for you to bring in a different literature into the explanatory evaluation framework. And visually, we are seeing that this is the uncertainty of this explanation. Now, let's take a little bit more of a mathematical viewpoint on why this uncertainty in intervenability can exist. If I have a y given Sx, which is a masked input, the idea is that if I want uncertainty, then there's a variance aspect to it. So a variance of y given Sx is going to be my predictive uncertainty. I can use a very simple variance decomposition, which is V of expectation, variance of expectation, and expectation of variance in order to construct this kind of a variance decomposition for my predictive uncertainty. Here, Y is essentially the prediction, V of Y is variance, Sx is subset of data, or think of it as some intervened data, some mass data that can exist. Expectation of Y given Sx is expectation of class given a subset, and V of Y given Sx is variance of class given all other residuals. Now, in the beginning, when we were discussing about these explanatory methodologies, one thing that we saw was we want our explanatory methodologies to have expectation of Y given Sx to be 0. The variance of this expectation of Y given Sx to be 0. The reason being that if I mask a particular image, pass it through, and I pass the entire image through, I want the same I want the same prediction. So the variance of whatever that prediction is going to be 0. Ideally, I want it to be 0. Right? When we were talking about initial stage, the expectation of masking, we talked about E of Y given Sx2 is greater than E of Y given Sx1, which basically means that my evaluation methodology has chosen that explanation, which is always giving me the same Y. So the variation of that Y is going to be 0. My evaluation methodology has basically promoted those explanations whose first terminology here is going to be 0. The only uncertainty is now coming from the right-hand side, which is that the expectation of V given Y, expectation of variance given of Y given S of X. So key observation here is that visual explanations are evaluated to partially reduce this uncertainty within a neural network. The next one, of course, is what I just mentioned, which is the right-hand side terminology is where the uncertainty comes from. Uncertainty in explainability occurs due to all combination of features that explanation did not attribute to the network's decision. This is essentially nothing more than residual. So I could have chosen one more pixel on the right-hand side, right? But I did not choose it. And that is what I mean by residual. Anything that I did not choose when I was choosing my explanation is the residual in this particular case. And effect of that is what needs to be there within the uncertainty framework. So the effect of a chosen intervention can be measured based on all the input interventions that were not chosen. Now, I think we have agreed in terms of causal analysis that we cannot have all possible interventions within a neural network. The only way we can now analyze it is by making a statement something like this. Effect of a chosen intervention can be measured based on all the interventions that were not chosen. So it's like a not operator, essentially. We know that there is a complete set of interventions. We can only do 5 interventions. What is the effect of the other interventions is something that we need to calculate. So let's look at this again from a same perspective of explainability. What that essentially means is we're bringing back this slide. So in this particular case, for the bull mastiff, if explanation is something like this, one thing that you can observe is that snout is not as highlighted as the jowls within the explanation, but that's problematic, right? Snout is an important characteristic that is used to differentiate against other dogs. The fact that the explanation is not showing this snout within the heat map is a problem. Or maybe problem is not the right word, but that creates some a doubt in our minds, essentially, whether this is a good explanation or not a good explanation. That's where this kind of uncertainty comes into picture. So not chosen features, again, unfortunately, are interactable. There are infinite number of interventions. So how do we calculate the residuals of all these interventions? So this is where, the formula helps us. We want the expectations of variance of y given Sx. In other words, we want to find those interventions where y changes. We need v of y given Sx, right? Otherwise, if y remains the same, variance is going to be 0. So we want v of y given Sx. So this is where the contrastive explanations, where we backpropagate the wrong classes. So we backpropagated with y1, y2, y3, or wrong classes are q1, q2, q3. We can backpropagate against all the other classes, and we only have n classes. In ImageNet, for instance, that's about 1,000 classes. So you can get 1,000 contrastive explanations, take the variance across all these explanations, these contrastive explanations, and you'll be able to get this kind of a normalized output. Essentially Q1 to either QR or all 1,000, you take the variance across each pixel value, normalize it, and the output that you get is essentially this kind of uncertainty map. So now, based on this, again, our goal was to talk about explanatory evaluation. We can ask the question, is GradCam better than GradCam++? Is something like a Swin transformer more reliable than VGG16? So we need some objective quantification of these intervention residuals, right? So let me show you this example over here. So we have GradCam, GradCam++. Not much can be derived from guided backpropagation, but then there's smooth grad as well. So one metric that we can use on top of the explanation and uncertainty is something like intersection over union. If a particular region between the explanation is the same as uncertainty, then that means that the network is very uncertain about its own intervention. The region that it is uncertain on is the region that it is using to explain, which is not good. This is exactly not what we want from a neural network. So we want the IOU to be as less as possible. So higher the IOU, higher the uncertainty in explanation, or less trustworthy is the prediction. And just to show you what that means, if I were to show you this kind of, here on the top 3 images, the network has the correct prediction. So it said that this image is that of a bald eagle, I believe. And if you look at the GradCam explanation and the uncertainty is generally around this kind of thing. If you look at GradCam++, however, there's a lot more intersection. So GradCam++ is a little bit uncertain of its own explanation compared to something like GradCam, right? Now compare that against the images at the bottom, which is in this case this sled and snow dog, I believe. I think this was supposed to be a dog, but the network interpreted as a sled. So essentially it was an incorrect prediction. What you'll notice is that for incorrect predictions, a network is generally very unsure about itself. Even though its explanation is something like this, the same regions are where the explanation uncertainty also exists. So if you look at the IOU for this particular case, there is a lot more intersection over union regarding the between the explanation and its own uncertainty than compared to whenever the prediction is correct. And you see that in the next one as well. This was a bakery, but it was an incorrect prediction. I don't remember which prediction that was. This was for, I believe, VG16 architecture. And you'll notice in this particular case that the overlap is a little bit more compared to something like things where the explanations and the uncertainty are different when the prediction is in fact correct. So that is one objective metric. Another simple objective metric that you could use is something like SNR, signal to noise ratio. So if you add a lot of noise within the image, there will come a point where your correct prediction will become an incorrect prediction. And at that particular stage, your network is still trying to explain something. GradCam or GradCam++ is still trying to explain something. In that particular case, you can see that there's a lot more intersection over union between your uncertainty and your explanation. Also, the SNR is also very high. Something like BG16, SNR is all over the place, versus something like Swin transformer, not as much as the BG16 that exists. So there's like specific numbers in the paper, but I won't go through the numbers. It's not as important as the overall concept, which is that don't just look at explanation, also look at uncertainty, try to combine the two and get some statistic. In this case, I'm showing two statistics. One is intersection over union, another one is SNR, but I'm sure there are other kinds of statistics that we can use and come up with essentially to evaluate these kind of explanations a little bit more. So these kind of residuals must be analyzed intelligently to basically to trust or not to trust your predictions and inference. And not choosing interventions causes uncertainty within the chosen interventions, which is an issue. If you see the slides, I have all the data sets that uses these kind of benchmarks. I've listed a number of data sets, ImageNet C, for instance, ImageNet P. All these are very important, so you can go through the slides for these. We are running out of time. But this is essentially the last part, which is intervenability. The only part I have in the conclusion is I just wanted to end with a few memes. This meme we have already seen, novel data packs 1-2 punch. So it's very important for us to know when and how to train our data sets. Whenever we deep learning, we think that robustness is achievable. Adversarial images sometimes, take it away from us, and model deployed, but then test and train different distributions. There's a lot of work that goes on regarding the training process itself, which is optimization and data collection. But as soon as we come to inference, there's not as much work that has gone into it. But there is a lot of work to be done, thinking about how post hoc methods, how we can get some kind of reliability, how we can get some kind of robustness. It's very, very important that we think of it from the inference perspective as well. In fact, there's so much that the kind of questions we ask is also very important. Usually, whenever we think about explanations, it's almost always YP. But as soon as we start asking other kinds of questions, YP rather than Q, and what if, a different set and kinds of explanations and methods can come into picture. Lastly, this is my favorite, which is we are doing a lot of explanation, explainability, interpretability. But as soon as we look at how we are evaluating these explanations, what you're in fact doing is uncertainty at the very end, because all you're doing is, while evaluating explanations, you're just reducing or partially reducing the uncertainty. You're asking the network at what regions is the least amount of uncertainty exists. Okay, then this must be your explanation. That is all we are doing. So there has to be a much better analysis of explainability techniques itself. But yes, that is the end of the tutorial. So again, the slides themselves have access to all references that has been used, along with the materials are also available. So thank you. If you have any questions, please reach out. Sure, of course, yeah. Please drop me an email. I think that's... I think so as well. Separately, yeah. At the end of the day, we are combining. It's just that it's not explicit. That's the only thing. Thank you. Of course. Okay. Okay. My goal achieved. Yes, that's yeah. Thank you. Yeah. Yeah.
Thank you.
Thanks. Yeah.
Quite uncertainty. Do you think it would be useful as a filter to kind of say, very uncertain, or do you think it should be used more as like a tool for calibration or
so in this case, I'm very much biased towards the application is the driver of this particular case. So for instance, if we have like and this depends on the process as well, right? So if it's in a healthcare process, for instance, it's a very almost a flowchart kind of a way of trying to find a decision. And if in any place this flowchart is broken, you need to bring a doctor of perspective. So it's more like the first thing that you said, where the goal is you just use it as a filter essentially, where after a certain point, if the uncertainty is high, bring in a specialist, bring in a doctor. But there are other instances in autonomous vehicles, for instance, where I believe that it's more viable to do the second one, where you're just calibrating based on the surroundings and this one. Yeah, but I believe it's completely based on the application.
Okay.
Yeah, of course.
So I work with like object detection first. It's all very relevant.
Okay.
And interesting to me. Yeah, because we deal with like overconfidence, where it's just false positives and it's like 0.99 or something like that.
Sure. Yeah.
So I'm curious. It seems like there's kind of a trade-off between like inference time and a good uncertainty prediction. Like you could do that ensemble, but that's like running multiple networks at once, which is stuff.
Yeah.
I'm curious if there are ways to do an ensemble.
That's the Monte Carlo dropout. You could do that. So Monte Carlo dropout is specifically just that. So you could definitely try that out. Yeah.
Oh, so with Monte Carlo, you would keep the backbone and then just do dropout on that.
Exactly.
The latter part.
So usually, sometimes you can do dropout on all layers whenever it was trained, or you can just do the final layers. You can do some kind of a dropout, and you can do it n number of times and combine it in ways. So Monte Carlo dropout is a good strategy for that.
So I think you were mentioning like you would want to pay attention. Depending on the application, Monte Carlo dropout, you'd want to do maybe earlier layers or later layers. But with object detection, you're saying it's maybe the later layers.
Later layers for sure, yeah. Also, be very careful about the number of dropout itself. Like like 0.1, 0.2 is generally what we do, and usually it's dependent on the training as well. So if you've trained on 0.2, your dropout has to be 0.2 as well, because your weights have to adjust in a way. So at inference, but generally the issue then is that you don't know at training if you've done this. So while testing, what you would do at deployment, that is an issue. But even without that, depending on the kind of data, you probably, and the kind of network. So as I was mentioning in transformers, you want to make sure that dropout may be a little bit higher, because with 0.1, your dropout, nothing's going to happen. Everything is going to be like, you'll still get the same prediction over and over again. Yeah. So you want to increase the dropout. So it's more of a trial and error perspective, but once you have done the trial, you need to go back, retrain the model with that dropout and do it again. It usually works well.
That makes sense.
Yeah.
Okay. And then just one last quick question.
Yeah.
If you were gonna like rank the effectiveness of the different uncertainty measurement, you'd say that the ensemble's top.
Yeah.
And then dropout and then gradient.
Yeah, dropout and then gradients.
Okay.
Yeah.
The dropout and gradient pretty close to each other.
I think it also depends on statistics. I would rate dropout more than gradients. It's just that you need to have multiple forward passes, while gradient is more computationally efficient. It's just basically single pass and you'll get some results. That's it. Yeah, there's that trade-off. But yeah, I mean, if that is not an issue, dropout is probably more approximate than gradients.
Okay.
Any gradient.
Thank you so much.
Yeah, of course.
Great.
Yeah. Thank you. Yeah. Yeah. Yes. Yeah. I think it's there. In the slides, I don't think in the plots it was there, but in the tables it was there. Let me just go there. Where was this? So this is what you're talking about. Yes. You're right. Yeah.
This is particularly distinct.
Absolutely, yeah.
I was looking to see there's a plot which is like my train
in the paper, I think there is about tiny ImageNet. Tiny ImageNet is, so in the slides, I don't think I put it in, but tiny ImageNet is the distribution and test is the VBAR. So it usually works, but you're absolutely right. It's tougher in that scenario. It's much, much harder to do something like that, for sure, yeah.
But the human is interpretability.
Yeah. Yeah. Feature, factor, yeah. Yeah, in this case, yes, I think I showed black, but usually it's the mean. Mean is the easiest, like yeah, solid gray, exactly. You're right. Yeah. Absolutely. So that in fact is worse. Like if you see the prediction, the ability of networks to handle this kind of noise is worse. That's why people just use gray, the mean as the best one. But you're absolutely right. So there is no accepted intervention on those masking that gives us a good result. Any intervention we do, we are always going to get a bad result. So I honestly, I don't think anything that we do is good. That's why I'm more inclined towards, yes, we're doing explanation, but let's just do uncertainty, because at the end of the day, we're still doing the uncertainty estimation within this explanation. So there has to be a kind of analysis between the two and connect the two to evaluate one and not the other, sorry. But yeah, you're right. I don't think there is no accepted way of masking them. Yeah. Quite a lot. I think a lot of work right now is using language in order to do the explainability part. The only issue I personally have with that is the fact that one is a model, which is susceptible to a lot of hallucinations by itself. So we are using a model that is susceptible to hallucinations to explain another model that is giving us some kind of an output or prediction, right? So there is this kind of inception of more models that is happening. And if we are specifically talking about like explainability literature, again, I think that is definitely the way forward. It's just that we have to be very careful in analyzing one, analyzing the other, and then combining the two, instead of combining the two and then thinking, okay, what should we do about them together in this thing? So I'm more of a module kind of a person rather than saying combination, go forward in this one. But yes, language is an important part of explainability.
Thank you so much.
Of course.
Yeah.
Nice.
I have just two more questions, but are more technical. Maybe you don't want to answer.
Okay.
So when I saw that your paper about two-stage approach was at the NeurIPS, and then you started just publishing on like the International Conference on Signal Processing, right? And is there some kind of motivation behind this tendency?
So the signal processing part is more designed towards, so if you read the paper specifically, it's more designed. Oh,
sorry to interrupt you, but by 6 o'clock before 6.
Okay, we'll do that. Yeah, of course.
Thank you so much.
Yeah. Because the paper is written more from a signal processing perspective. If you read the paper itself, the voice paper, I think you're talking about the voice paper, right? The uncertainty in this thing, and the gradients paper. So if you read the paper, it's more from the orthogonality of gradients. So the mathematics of it is more signal processing than compared to something in NeurIPS, which is more related to the machine learning aspect of it. So that was the main difference over there.
But do you personally like prefer to write in this way, or?
For me, I think I come from a signal processing background, so it's easier for me to write something there than something in NeurIPS, let's say.
Okay, but this is like I don't want to I like writing in signal processing
Oh,
language.
I would love to write in Euribs as well, except that the amount of the way the reviewing is done in Euribs is very different from signal processing perspective. So it's more randomized in terms of the reviewing process in Euribs for me to get, let's say, accepts over there than compared to something signal processing, where I know for sure that this writing is very good for something like signal processing magazines or journals or something.
So you just consider the conference to be pretty like uncertain in,
yes.
in assigning
yes.
the grade review.
Yes.
Okay,
yes.
Right.
And I'm not a PhD student anymore, so it's not like I
Okay,
want
right.
new
You just do
yeah.
like
Yes. Exactly. Yeah.
Okay.
yeah.
So, cards to you, and I wondered if you have actual business relationships where you use XAI or
Nothing.
no. So
No,
people
I'm just here. I love XAI, and so there's no I'm no business.
Okay, so just for the art.
That's it.
I like this. But people are like, they must what do you think? Or is it like?
I think XA is extremely important in all business, like industrial applications, right? Especially, I mean, every single, let's say autonomous vehicles, for instance, like the manufacturers, it's important for them to build better models. Insurance companies, it's very important for them to see which is this thing. So every aspect of business, wherever AI is used, if it's liable to be sued, they need an explainability component.
And they still don't come to you.
Okay.
So,
yeah.
I just wanted to
yeah. Thank you. Thank you. Thank you. Hi. Yes. It's just L2 norm. So L2 norm. So we are just taking squared, we are just squaring it, and we are just taking the sum of it all. That's it. So we just call it energy because I think coming from a signal processing background, it's called energy, but it's just L2 norm, mathematically L2 norm. That's it. Oh, no. This is simple L2 norm, not anything related to the energy models. Yeah. Energy models also, I mean, that also there's an out of distribution detection called energy, right? I think in the paper we compare against it. It's different. It's a little bit different than the energy that we were speaking of. Yeah. Yeah, of course. Oh, thank you. Thank you. Hello.
So almost all the methods are class specific methods. But then if you look into
Okay.
So in that, when the model is performing well or when the model is not performing well, how do we understand what aspects the model is doing?
So if you're coming from that perspective, right, you need to decompose it into, let's say, 3 components. One would be color, one would be texture, another would be shape or something like that. So you can decompose it into those 3 components and you can find some kind of explanations that is based on that if you don't have color. Very recently, I think last month, we published something on that. So it was based on representation learning, where you have access to no classes. But if you remember the RISE method that I was talking about, so if you want to do color, instead, RISE, what it does is it randomly takes out patches, like 6,000 patches out, right? Instead of taking them out, decolorize those patches, pass it through the network, and see what the result is going to look like. So that will give you like the color components out of it. So anything with natural images where you don't have classes, you still have access to these very simple like image-based metrics like color, texture, shape. If you want, I can give you the name of the paper, but then but essentially you can use that in order to construct these explanations, which is completely class independent.
One other question.
Yeah.
So I am working on RGB and thermal image future. So here we try to match the features of RGB with the thermal imagery.
Okay.
So when you have a thermal component also, which don't have color and texture.
Okay.
So how do you?
So I'm not very familiar with the thermal imaging. So it's similar to the Connect data, right? It looks similar to the Connect data, but it's not that, of course. It's not the depth
kind of
data.
temperature.
Yeah, sure. Yeah. Honestly, I don't know. So if I were to think of that, what is the image feature that would depth, gradient of texture, maybe something like that? Not the gradients I was talking about, but the gradient in which it changes is where the depth, right? So maybe something related to the gradients. So kind of quantize it based on something and remove certain quantizing parts and then see what the results are. But I don't expect too good results to come out from there, because all these explainability methods, even whichever neural networks, it takes that fine-grained information. That is what is the bread and butter. So if that is not there, it's really hard for this one. Yeah, exactly. And that is very important. So without that, I'm not really sure. Yeah, of course. Oh, explaining representation learning with perceptual components. Of course.